University Talwandi Sabo, under the leadership of Baba Iqbal Singh Ji, Kalgidar Trust Badu Sahib, has started its sixth academic session this year. The mission and vision of this university is not merely to impart literacy, but also to provide high quality, spiritual value based education. The Akal University has mandated to uphold the three basic principles of higher education, namely teaching, learning, and research. The ultra-modern facilities for teaching and research are the hallmark of this university. Now, I would like to give a brief introduction about Department of Chemistry also. Our Department of Chemistry has been established to foster education and research to meet the growing demand for qualified and efficient individuals in the country and across the globe. The department offers undergraduate and postgraduate courses with honors stream. The department strives to provide national ambience in local setting. A mentor-based teaching method is followed where each student is personally guided so that he or she can reach its true potential. Special coaching classes for NET exams are routinely conducted. Research projects and practical-oriented teachings are supported with the help of an able lab infrastructure. Staying true to our social commitment, the department has conducted research projects on various local issues such as water pollution and soil pollution. The department is supported by an exceptionally qualified and motivated faculty with a strong commitment to teaching and research. All faculty members hold PhD degrees, with most of them having postdoctoral experience from reputed institutes in India or abroad. Ladies and gentlemen, in previous years, our department has organized a number of webinars, including nanotechnology for healthcare, carbon dioxide utilization, and applications of bioinorganic chemistry. These webinars provide a venue for stakeholders working in chemistry to share practices, ideas, and resources. To maintain the continuity of learning, we planned today's webinar on recent trends in green chemistry to benefit our students and students across the nation. Sustainable and green chemistry is very simple term in just a different way of thinking about chemistry and chemical engineering can be performed. To, perfect, to protect our mother nature from the ever-increasing chemical pollutants, scientists are restlessly developing and modifying the chemical processes to make them sustainable. Under this preview, interaction with distinguished scientists might bring opportunity to learn many new things of today's research. So this one-day webinar on recent trends in green chemistry will be very helpful for all the learners. So the main aim of webinar is to offer an understanding of recent developments using green methods. Pupils working on this field of green and sustainable development will be benefited through this webinar. With deep, sincere sense of appreciation, I am grateful to all our distinguished speakers for accepting our invitation and sparing their valuable time for our learners. With these words, I extend my warm welcome to our honored speakers of today's webinar, Professor Rakesh Kumar Sharma, Professor Asish Ranjan Das, Professor Anil Kumar Gopinathan, and Professor Basudeb Basu. Respected sir, thank you for accepting our invitation on such a short period of notice. I would also like to give my sincere gratitude to our Honorable Vice-Chancellor, sir, who encouraged us and support us to organize this webinar. Now, I would like to request our uh, esteemed Honorable Vice-Chancellor, sir, to say few words for this inauguration session. Over to you, sir.
So, thank you, Dr. Sandeep. So, on my own behalf and on behalf of Akal University, it's my proud privilege to extend very warm welcome to all the participants in this one-day webinar on recent trends in green chemistry. So, first of all, I am grateful to Dr. Sandeep Kumar, HOD of the department, and the other faculty member for taking this initiative, for organizing this seminar, and the brain behind this, and the person who is really planning, executing, contacting the resource persons for the same is Dr. Bhuvan Banerjee. And I am highly appreciative of him for taking this initiative for organizing one-day webinar on the very contemporary theme which touch all of us and very intimately related with the sustainable development and sustainable future of the mankind and sustainability of our ecosystem, sustainability of the universe. So I am especially grateful to the four distinguished leading scholars and if I am not wrong, best brain in country on green chemistry, Professor Rakesh Kumar Sharma ji, FRSC, Coordinator Green Chemistry Network, Delhi University, Dr. Asish Ranjan Das from University of Calcutta, Professor Anil Kumar Gopinathan ji from Mahatma Gandhi University, Kottayam, Kerala, and Professor Basudeb Basu from University of North Bengal. So, Sir Sharma ji, I am so grateful to you for sparing time from your busy schedule and be with us and to enlighten the faculty member, the people who are joining this webinar online, and the young scholars who are the future of this country so far as the development of chemistry and development of knowledge is concerned. So we are really grateful to you for sparing time and agreeing to be a part of this. Definitely, everybody would be left more enlightened, more aware about the various facets of the green chemistry after listening to such towering personalities in the green chemistry, these four distinguished scholars and the other participants. So, on behalf of Kali University, Professor Sharma, I would like to request you that we are a young university. We are just the beginners in this area, and we really look forward to towards yourself, sir, and towards other scholars. For we seek help from you to organize if possible, that as and when the situation permit us to organize some seminar, some conference at this university, probably that is how a very distinguished leading scholars from very old and established university can help the young university to grow and come up to your expectations, sir. So I would not like to stay between the speaker and the participants and without wasting time. So I pass on and I again express my sincere gratitude to Professor Sharma and other three distinguished scholars for agreeing to be a part of this webinar. And again, thanks to everybody who contributed in organizing this one-day webinar, and special thanks to Dr. Banerjee for his initiative. So thank you, sir. Thank you.
Thank
Thank you, Honorable Vice-Chancellor, sir, for their words of encouragement. Now, I would like to request Dr. Bubin Banerjee to start the proceedings of today's webinar. Dr. Bubin Banerjee.
Thank you, Dr. Sandeep sir, and thank you, Vice Chancellor sir. So, to introduce Professor R.K. Sharma sir, it is my pleasure to welcome him because he is he teach me during my MSc at Delhi University. I'm a direct student of sir. So thank you so much, sir, for your throughout guidance and support. So to introduce sir, let me share one slide. Just a minute. Yes, Professor R.K. Sharma sir did PhD from University of Delhi and then postdoc from Kumamoto University, Japan, and then Institute of Medicine, Medical Science University, Tokyo. Then he is the right now he is the coordinator of Green Chemistry Network Center, Delhi. He is the fellow of Royal Society, that is FRSC, and honorary secretary of Royal Society Chemistry of Chemistry, London, North India section. And he is the honorary professor of Deakin University, Australia. He is the editorial. He is in the editorial board member of current research in green and sustainable chemistry, published by Bentham and this Elsevier. He edited a number of books. One is Hazardous Reagents Substituents, published by RSC, Silicon-based organic and inorganic hybrid nanomaterials from World Scientific, and an introductory text on green chemistry for undergraduate students, published by Elsevier. Professor Sharma's research interests focus on the development of nanostructured catalysts for diverse applications. Recently, he has published more than 160 research publications. All are in high impacted journals like Green Chemistry, impact factor around 9, Dalton transaction, came from materials horizons, ACS sustainable chemistry and engineering, etc., etc. He has supervised more than 41 PhD scholar, PhD and MPhil student. He has and he is the he received award honorary fellow by National Environmental Science Academy. And so, with this short introduction, I'm welcoming you, sir, once again, and thank you so much for giving us this opportunity to hear you that from, and our participants will definitely learn many things from your research experience. With this, I am thank you once again, and over to you, sir. Now you can share your slide and please start your lecture. Thank you so much, sir.
Thank you, Dr. Bhuvan. And first of all, I would like to thank Vice-Chancellor Professor Gurmail Singh for inviting me, and Dr. Bhuvan Banerjee also for approaching me for this lecture. I'm just going to share my slides with you. It's not coming. Are you able to see my slide?
Not now. Right now, it is blank, sir. White page. Not
Just
the slide is not coming.
well, again, I will share that. So again, it's some problem in sharing. It's not showing my slides.
Sir, you please open your slide in the background. Don't minimize it, and then come in the this Zoom and share screen option. You click on.
Yeah,
Please don't minimize it.
I have already opened it in the background, and just I'm sharing. Yeah.
Yes, sir. Now it is visible. Yes.
Okay, so now it's visible. So as you can see, I'm going to speak on green chemistry education for a sustainable future. I'm from Department of Chemistry, University of Delhi. We have a green chemistry network center established in our university, which is working for the popularization of green chemistry, and a little about this center, a green chemistry network center established in Delhi University under the recommendation of a panel of world leaders headed by Professor Paulina Stas, and this man is known as father of green chemistry. And the aim of this network center is to build a network all over India, green chemistry network, preparing and disseminating green chemistry educational material, designing training workshops, taking up green chemistry research projects. We had research projects from CSIR, UGC, DST, DBT, industry, and recently we got a major project from Ministry of Textile for setting up Green Chemistry Network Center laboratory. In my talk today, briefly, I'm going to touch about these activities also. But before that, I'm just going to share with you a recent news from Chemical and Engineering News. This shows the importance of green chemistry. You can see recently, this came in January 5th issue of Chemical and Engineering News. Recently, the US Congress decided to bring a legislation, sustainable chemistry legislation, and they said that all the federal grants will be given which will promote green chemistry concept. So this shows the importance of green chemistry. But before going to green chemistry, let us see what chemistry is giving us. You know, this is the chemistry which is not only extending the length of the life from 47 years in 1900 to 75 years in 1990, but also increasing quality of life by providing so many things. You can see. So we chemists are making world worth living. But there's another side of chemistry. Chemistry also leads to toxic world. Chemistry also leads to waste disposal, pollution, disease, toxic emissions, landfill. And according to this Nobel laureate, Richard Smalley, who did a survey in 2002-2003, that the humanity's top problems for the next 50 years are energy, water, environment, and food, and more serious problem is due to the population growth. He said 7 billion people in 2011, and now by 2050, this is going to be 9+ billion people. So this is a very serious problem in countries like India, where the population growth is too much. And there's a very interesting comparison. If you can see about the population growth, whole UK's population is equal to one state population, Rajasthan. Same with Brazil is equal to Uttar Pradesh. So you can see the comparison. France population is equal to Madhya Pradesh population. So population growth is a very serious problem in India. And what is happening, nature provides us the resources. We are consuming resources and creating waste. And again, nature converts this waste to resources, and this way the cycle goes on. What we are doing, we are exceeding the carrying capacity of the earth We are using resources and creating waste faster than the earth can take our waste and convert them back into the resources. So because of the population growth, what is happening now, we are just converting resources into waste. We are consuming resources, creating waste. So this is now just one way. We are consuming natural capital rather than just the interest. So now the question arises, can green chemistry reverse this error or not? So let us discuss about this also later on. You know, this looks like a graphic art, but this is not. Take a more closer look, a more closer look, a more closer. So, 2 million plastic bottles discarded every 5 seconds in US, and 86% of plastic bottles in US end up in landfills, taking 1,000 years to biodegrade. You can see here, there's only generation, no recovery at all. And the more serious problem of this plastic contamination is that 90% of floating debris in ocean is plastic. And this is projected to grow tenfold in 10 years. Even plastic found in 48 to 86% seawards and mammals. And more serious problem with this is this plastic. We are using even the plastic bottles for drinking water. And these plastic bottles, they are containing a potentially harmful chemical bisphenol A. And the release of this bisphenol A creates problem. And recent research says that this BPA linked to breast cancer in women, brain disease or brain damage in children, obesity, heart disease, etc. And even then, we are drinking water in plastic bottles. Another graphic art, if you can recognize this. Take a more closer look. A more closer look. 426,000 cell phones retired each day in US. And India is the second largest mobile phone market in the world after China. And this e-waste is very dangerous. Even US, what they are doing in terms of recycling, between 50 to 80% of e-waste collected for recycling in the US are not recycled, but very quickly placed on container ships bound for destination like China or India. And this e-waste, according to the US Department of Toxic Substance Control, they determine that the most electronic devices are toxic based on 1,000 different toxic substances in e-waste. All of these are toxic. All of these, like copper, antimony, cadmium, mercury, which can be poisonous to people and wildlife. And even there's news came in the Times of India that Delhi is the second largest producer of e-waste in the country after Mumbai. Even 3-4 times I was invited by Doordarshan for a live show. And there we have discussed about this green chemistry and impact of waste on environment. So a big question before us is, within the next 50 years, how can we provide 8 to 10 billion people with energy, water, food, quality of life and future technology, and that is without global warming, without resource depletion, and without toxics in environment. And one of the answers from my side is green chemistry. So I'm going to elaborate this also. Now the question arises, what is this green chemistry? And why are we talking now about green chemistry? So the first question, what is this green chemistry? I'm just going to define green chemistry by just taking one slide and one relation. You know, the risk is a function of hazard and exposure. If you want to minimize risk, either you minimize exposure or you minimize hazard. And the traditional way of minimizing risk is by minimizing exposure, putting gloves or safety glasses or helmet, lab coat. This is the traditional. But if you can reduce or eliminate this hazard, you can minimize the risk even if there is any accidental exposure. And this is the approach for green chemistry. So green chemistry is defined as the design of chemical products and processes that reduce or eliminate the use or generation of hazardous substances. So this is the definition of green chemistry. You know, in 2005, Nobel Prize went to green chemistry. And see the words of Nobel Committee. They said that this is a great step forward for green chemistry, applying basic sciences to the problems of man, society, and environment. So this proves that the best chemists in the world are doing green chemistry. This is a book written by the two founders of green chemistry, Paul Anastas and John Warner, the Green Chemistry Theory and Practice. This was published by Oxford Publisher, and this is already translated into several languages. And this book is very good book for beginners. And this book is containing 12 principles of green chemistry. And these 12 principles are actually 12 tenets of green chemistry. Even these 12 principles, they provide a framework for design of new material, product, and processes. And systematic integration of these principles is key to achieve genuine sustainability for the simultaneous benefit of environment, economy, and society. These are the 12 principles of green chemistry, but I'm not going to touch these 12 principles because explaining these 12 principles will require at least one semester. So I'm not going to touch this. Now, the main problem or the biggest challenge of green chemistry is to convince people to adopt it. And we started this mission of convincing people to adopt green chemistries from very back from 1999 onwards. 99, we had organized a national symposium on green chemistry. Then in 2001, IUPAC International Symposium on Green Chemistry was organized, where you can say the inaugural session was chaired by Sheila Dikshit. That time she was the chief minister. And Professor James Clark, is famous man of green chemistry from University of York, UK. This one was Terry Collins, famous man for catalysis work. So they all came, but what was there, the people were, that time, were reluctant to change. They don't want to do green chemistry at all. They used to laugh at us. They were saying that if there is any green chemistry, then there should be a red chemistry, pink chemistry, yellow chemistry. But we continued for the popularization mission, and we knew that change can come much more slowly than anyone would expect. Simply stated, people don't like to do things differently from the way they have done them before. They don't want to come out of their comfort zone. And new ideas and new perspectives often face harsh opposition. And there are very interesting examples to support this. You know, the Manleaf, the great Manleaf, inventor of periodic table, refused to acknowledge the existence of radiation or even electron. The great Einstein rejected quantum mechanics. He said quantum theory is certainly imposing, but an inner voice tells me that it is not yet the real thing. And this is the third example, which is much more interesting. This Nobel Prize winner, Daniel, he got the Nobel Prize by discovering this type of crystals. He got the Nobel Prize in 2011 by discovering this type of quasi-crystals. He said when he discovered these type of crystals, people just laughed at him. And even after telling Daniel to go back and read crystallography textbook, the head of his research group asked him to leave the group for bringing disgrace on the team, and I felt rejected. So this happens when you are starting a new thing. But we continued on this popularization mission, and these words of Mahatma Gandhi actually encouraged us that first they ignore you, then they laugh at you, then they fight you, and then you get. So we continued for the popularization mission. And we found that if we want to incorporate, if we want to popularize green chemistry, if we want to incorporate green chemistry principles into industry or academia, then the best way is by organizing workshops, not by organizing conferences or symposia. So the first workshop we had organized with the support of Indo-US Science and Technology Forum. And this workshop was inaugurated by DSC secretary at that time. And this man sitting on the right delivered the inaugural lecture. And this man is known as father of green chemistry, Professor Paul Anastas. So that time he was the advisor to President of US or American President, White House, and he came from Washington all over for delivering the inaugural address in this workshop. And not only Paul Anastas, John Warner and other world leaders of green chemistry, they also participated in this workshop. You can see the Terry Collins, famous man for catalysis work, got the US Presidential Award also. This is Dr. Mary Krichoff. She's Director, American Chemical Society's Green Chemistry Institute. This is Robin Rogers, famous for ionic liquid work. John Warner, and then on my left is Professor Paul Anastas. And they all recommended that if green chemistry is to grow in India, then there should be a green chemistry networking of different centers. So we started working on networking, and we got IUPAC Cameron GCI Den Grant Award continuously for 3 years for doing this networking activities. And we have designed a simple form which anyone can fill this form, just answering few things and answering the main question is, I wish to be a member of Green Chemistry Networks because, so 100 words, why you want to join this network, and there's no fee for joining. Now, for popularization, we are going to schools also. This is the symposium organized by all the schools of Delhi and Gurgaon. You can see I've delivered the inaugural lecture. And every year we are organizing training workshops on green chemistry for students, educators, and industry. So this is 2009, 10, 11, and this is in 2015. Even Dr. Avtar Matharu from University of York, and even Dr. Constable from ACS Green Chemistry Institute participated in this. And the valedictory lecture was delivered. This was the group of participants, and valedictory lecture was delivered by Dr. Ashutosh Sharma, who is currently Secretary DST. We are not only in Delhi, we are organizing activities all over India. We are going, delivering the lectures and organizing activities. So you can see Nagpur, Assam, Punjab, Hyderabad, Gujarat, Rajasthan, Gujarat, Sikkim, Mizoram, Punjab, UP, Kanpur. Then this is Garhwal, Central University, Garhwal, Himachal Pradesh. This was covered by all of the media. Then Bihar Association of Chemistry Teachers organized a conference, seminar, and I have delivered the keynote there. Patna, then Himachal Pradesh, Rajasthan, Kerala, Punjab, Udaipur, Jaipur. This is again international workshop. This is in Jalandhar, Punjab Inspire program, then Punjab University, Chandigarh. Now the question arises that I'm touching on going and delivering all over India. What is the result out of this? Something is happening because of this or not? Is there any benefit of doing all this? And I'm going to share some output about these activities. A real world case of green chemistry in Indian pharmaceutical industry, where wealth came from waste through green chemistry, and our role was there. So I'm just going to share with you this about this real world case. As you know, green chemistry is reducing waste, reducing materials, reducing hazard, reducing risk, reducing energy, reducing environmental impact, reducing cost. And everything is followed in this real world case. So what was that real world case? I'm just want to share with you. All of you know ranitidine HCl is an important and cheapest anti-ulcer drug available to common man. And SMS Pharmaceutical, these are the producers of this drug, but SMS Pharmaceutical Hyderabad was the world's largest manufacturer of this drug. And what happened? The Pollution Control Board instructed these two companies, SMS Pharmaceutical and Saraka, that you stop production, shut your plant, and stop production due to the emission of a gas, toxic gas, methyl mercaptan, as waste from manufacturing process. So this was the whole manufacturing process, traditional method for production of ranitidine. You can see this is the raw material, DMSO, and then the production of ranitidine followed by methyl mercaptan, which is a toxic gas. And this is very horrendous smelling gas. You can smell this gas even at a very ppb level. You can smell this gas. So these are the toxic effects of this gas. And this was the industrial practice to treat this gas, traditional practice. And you can see so much input and output, and even then there is release of methyl mercaptan. So the green chemistry came into the play. What a green chemist who was working with us for popularization of green chemistry, Professor Meher K. Chaudhary, who was the dean and head that time at chemistry department, IIT Guwahati, he has developed a catalyst for this industry, and that catalyst did the wonder. What catalyst did? Converted methyl mercaptan to DMSO. And DMSO was the raw material they were using. And so that catalyst converted the toxic gas to raw material, and they have again used that raw material in the production of ranitidine. So the cost came down, 40% reduction in the cost. So you can see the advantages: low capital cost, reduced cost of production, nominal supervision, highly protective, and environmental friendly. So this industry, actually, SMS Pharmaceutical, they had written me a letter, an invitation letter I have received from this industry. And in that letter, they have invited me to visit their plant. And they said, being inspired by your speech in the conference on green chemistry held at IIT Guwahati, we have concentrated on one of the burning problem of Hyderabad world drug industries. So the same way as I'm delivering lecture here on the green chemistry popularization, the same way I was delivering the lecture in the conference at IIT Guwahati. And these industry people, they were attending that conference, and they thought that the green chemistry might help them, and green chemistry did help them. So I visited their plant also. You can see this was the plant. Everything was clean, no smell, nothing was there. They have explained all the process. Um, you can see, and not only me, with me there were the two pollution control board people. This man, Dr. D.C. Sharma, additional director, Central Pollution Control Board, and this man is MD and Simha, member secretary, Karnataka Pollution Control Board. So they were also visiting that plant, and they were so happy after seeing this process that they requested me that if you are going to organize another workshop on green chemistry, please invite us also. So this case, this real world case, we have we have given on our website. So when we returned, and after a few days, we got a mail from Dr. Reddy's lab. You know, the Dr. Reddy's lab is a major pharma industry in India, and it was written that, dear sir, ours is a pharmaceutical industry manufacturing ranitidine, and as for the website, there is a development on wealth from waste. Say methyl mercaptan gas is converted to DMSO. Can I know more details on this? So we have guided them, and they have also putting up a plant in Hyderabad. So these are the 12 principles of green chemistry. And you know, one of the very important principle is use of selective catalyst. And according to the Nobel Prize winner or Nobel laureate, very Sharpless, catalyst is the engine that drive the development of chemistry. So he said catalyst is very important for the development of chemistry. And not only this, The catalysts are essential in the synthesis of more than 80% of the chemical industry products. And one of the great thing about catalysts is that even a slight improvement in their performance can be worth millions. So this can be supported also with the Nobel Prize winners. You can see so many winners of Nobel Prize worked on catalysis area. See, 2005, 2001, 1973, 1963, 1918, 1909, 2010, and Nobel Prize awarded for palladium catalyzed organic synthesis. So this shows that catalysis is a very important area. So my research group is also working on catalysis area. And we know there are two types of catalysts, homogeneous and heterogeneous. Homogeneous catalysts are very good, very active, very selective. And heterogeneous are having advantage of separation and reuse. So what we did, we have combined the activity and selectivity of homogeneous catalysts and reuse or the ease of separation of a heterogeneous catalyst. And we have reviewed our work also and published in green chemistry, coordination chemistry reviews. These are last 2-3 years publications from my group. You can see the Dalton transaction, material horizons, inorganic chemistry, then chem, suschem, chem, cat, chem, RSC advances, material chemistry frontiers, material horizons again, then chemcom, ACS omega, then chemistry select, industrial engineering chemistry research, ACS, Nature Scientific Report, green chemistry, then this is chemistry select, ACS omega, then chem plus chem, green chemistry, ACS sustainable chemistry and engineering, new journal of chemistry, then again chem cat chem, general material sciences, green chemistry, catalysis science and technology, Dalton transaction, again green chemistry, general material chemistry, A, catalysis, communication. And I'm very happy to share with you that we got a mail from the editor of this Green Chemistry Journal. Green Chemistry Journal is a very high impact factor journal of Royal Society of Chemistry. And in this journal, I got mail actually by the editor of this journal that I'm emailing to let you know that your article, our article on this work, our catalysis work, is the most downloaded articles in green chemistry. So I'm very happy to share with you that at least our research was recognized worldwide. Even we have published a paper on a copper-based magnetic nanocatalyst in Nature Scientific Report, and this came, we got a mail from chief editor of Scientific Reports Nature, that our article is in the top 100 scientific report chemistry papers. And recently, we have published an article on recent development of covalent organic frameworks, synthesis and catalytic applications in material horizons, which is having impact factor 12.31. And we got a mail from the editor that our article is in the 2020's most popular article. So I'm happy that at least our research is recognized. So considering the popularity of our work, we have published or we got an invitation from World Scientific publisher to write a book on this. So we had written a book also on our work. Wherever we are going, we are showing this impact factor comparison to industry or academia. See the pure chemistry journals 1.9 to having impact factor 3.2, and all the green chemistry journals uh, they are having high impact factor like 9.4 something for green chemistry. So this also shows the importance of green chemistry area. We are going to industries also. Uh, we had organized a workshop at Mumbai for the industry where around 300 chemical industries participated, and uh, John Warner and Paul Anastas, they also participated with, you can see Dr. Ramaswamy, that time he was a DST secretary, also participated. I'm also getting an invitation from industries. This is, I was invited to deliver the opening lecture in this Green Technologies in Unit Operations seminar organized by um, Gujarat University, Ahmedabad, and Pollution Control Board. So I've delivered the opening lecture. And this afterwards, this came in media also. Media also covered this, and even our Prime Minister praised about this. As I said, Dr. Reddy's lab is a major pharma industry, and every year they used to organize a symposium on Science Day. So API Science Day Symposium. After this is in 2019, the symposium was organized, and in every symposium they used to invite one scientist or academician from all over India for delivering the lecture. So this time I was invited to deliver the lecture on green chemistry. Again, I was invited by JIST, Japan Advanced Institute of Science and Technology, to deliver the lecture on green chemistry. This is one of the world's largest symposium on analytical chemistry. So in 2019, the theme was enhancing analytical chemistry with sustainable solution. So they have included the role of green chemistry, and I was invited to deliver the lecture in this symposium, and I have delivered the lecture on green chemistry and water treatment from vision to action. This is another work, green chemistry work, which my group is doing. You know, this looks like a periodic table. Just you see, this is, and here these metals in red are actually exhausting. We are recklessly using these metals and throwing into the environment, and their life is now 5 to 50 years, and the others to follow, like these blue one are 50 to 100, like this. So the supply of metals are running out, creating challenges in the form of resource deficit. So what is needed, like, and this can be seen in terms of price increase. Since 2000, the price of copper has quadrupled and platinum tripled. The rare earth elements have collectively increased in the price by a factor of 20 since 2005. Indian price uh, rose a staggering 800% in 6 years. And this is case of the bulk metals, precious metals, and rare earth. So what is needed is to extract this and reuse these metals. Even, you know, the rare earth reserve is there in China. So this came in the newspaper also. Will China weaponize rare earth metals in trade war with US? So what US is doing, this came in Chemical and Engineering News. They are giving millions of dollars of grant to the industry and academia for the recovery of these rare earth from the coal. So rare earth recovery to extract valuable elements from the coal waste. So what is the issue here is the depletion of resource at alarming rate, and what is required is to recapture of metals highly desirable. So we are also working on this problem. We have developed some specific chelating polymers where we have immobilized, chemically immobilized a metal-specific chelating agent on inorganic polymer support. And you see this chelating polymer is so effective. This is the chromium solution, you can see by the color. And when we add this chelating polymer to this solution, this is absorbed by that chelating polymer, and you can take out and elute that out. Pure chromium can be eluted. You can see chromium after addition of, and we have patented also on this. And we have developed a bioreactor for online extraction of this metal like chromium. We got a major grant to develop this from Department of Biotechnology. So we have patented this bioextraction of metals and methods of working for the same. Even, you know, the Kanpur DAB college, very old college, invited me to deliver the keynote address. And you can see the Kanpur University Vice-Chancellor is sitting here. So Kanpur is facing very serious problem about the chromium, because tanny industries are there and they are using chromium and throwing chromium into the wastewater. So I have delivered the lecture on how can we extract the chromium out of that. And this came all over media, and you see the response. Around more than 5,000 participants were there attending my lecture. Even we had organized a CS workshop, and in that workshop, around 10 experts from US water technology or water quality expert, they came, and we have demonstrated our technology before them. You see the Duke team, this came in Times of India. Duke team claims to have developed a solution from chromium pollution. These are the other publications for other metal ions like palladium, and this is for other molybdenum, this is for lead. And we had written number of chapters, and even these are all chapters. And this shows, now we are working on a project, DST project, worth 50 lakhs, is to develop the magnetic chelating polymers, magnetic polymers, and see the role water containing chromium ions. And when we have added that magnetic polymer, you can see that can be taken out just by the use of a small magnet. This was the sanction letter of that project. Now, finally, I will end with the educational activities of our network center. We are, as I said, we are working on the education also. We have already incorporated green chemistry in undergraduate syllabus of Delhi University. 3 papers are already introduced in undergraduate syllabi. And some of the colleges colleges, very reputed colleges, are running add-on course on green chemistry like Miranda House or Hindu College. So they are running add-on courses and we are helping them to run the course. You see, this is the paper we have introduced, a general elective course paper, Green Chemistry, Designing Chemistry for Human Health and Environment. This is the paper, and this is general elective course paper, which the student can take of any stream, like commerce or art stream, they can also take this paper. We want to inspire the students that wherever they go, they should think in terms of green chemistry, in terms of green. And you see, in Central University of Rajasthan was the first central university in India. They started MSc Green Chemistry here, and we have designed the syllabus for them. I and Professor B.C. Ranu, we too designed the syllabus for them. This is a book we had written, an introductory text on green chemistry, which is published by Wiley. Recently, as I got the recognition from by this award and honorary fellowship, and this another book on for beginners, green chemistry for beginners, is going to be published by Stanford publication, and this is the forward was written by, again, the father of green chemistry, this book. You know, Journal of Chemical Education is the best journal for the teachers, for the students to learn about the green chemistry. For the academia, this is the best journal. And this is the world's premier chemical education journal published by American Chemical Society. And you will find a lot of material of green chemistry, even green chemistry experiments are published in this journal. So what we are doing, we are also designing experiments, green chemistry experiments, and publishing in this journal. This is recently we have published magnetic nanoparticle synthesis, and they are used as catalysts for degradation in green chemistry experiment. Then this is another experiment, preparation of gold nanoparticle using tea, a green chemistry experiment, so published in Journal of Chemical Education. And this actually, again, we got a mail from the editor that this is the most downloaded and most read experiment, preparation of gold nanoparticle. Even University of York, UK, they used to Green Chemistry Center for Excellence. They used to publish every month a newsletter on their activities. So in that newsletter, they have given our experiment as a breakthrough, nanotech. We have published a monograph on green chemistry experiments, and the foreword of this monograph was written by Professor Paul Anastas. This was released by the cabinet minister. You can see the Professor John Barner, Professor M.K. Chaudhary, Professor Chandrasekharan from IISc Bangalore, and funding received from DST for designing and revalidation of green chemistry experiment. You know, we are instructing students that, see, before starting the experiment, you just see the chemical you are using can be a high-risk chemical or environmental damaging chemical. So, first of all, you should look for MSDS, Material Safety Data Sheet. And this Material Safety Data Sheet is freely available on this website. Anyone can access this Material Safety Data Sheet. So we know that the major incentives of implementing green chemistry experiments are high safety, high performance, and low cost. We have considered the following criteria for judging the greenness or the potential of the new green chemistry experiment. So the criteria is that they should reduce lab waste and hazard, they should illustrate green chemical concepts, they should teach modern reaction chemistry and techniques, they can accomplished during a typical lab period, uses inexpensive greener solvents and reagents. So just one experiment, green chemistry experiment, I want to share with you. This is the extraction of limonene from orange peel. So, the extraction requires organic solvents, and these organic solvents are highly toxic. Just a list of organic solvents. So, they are highly toxic, highly volatile, fire hazard, costly. So, what we did, we have used carbon dioxide, liquid carbon dioxide for the extraction, and this was non-toxic, non-flammable, chemically benign, and for the instruments, it is very interesting. They know the carbon dioxide is a gas, is a solid also. But the question arises, how can it be used as a solvent? So we can show them by using phase diagram of pure CO2s and at different temperature, the state and pressure, just like this. This is the phase diagram. So this actually experiment requires a polypropylene tube, a coiled copper wire, dry ice from any ice cream stall, and orange peel. So what to do is just a copper wire was taken and coiled at one end, and a piece of filter paper was fitted in between the coil like this. Coiled copper wire and piece of filter paper was placed. And then a polypropylene centrifuge tube tapering at one end was taken and the wire was fitted inside it. So polypropylene tube was taken and wire was fitted. And the orange peel was grated using a cheese grater and put inside the tube. So orange peel was grated and put inside the tube. And this was topped with crushed dry ice and sealed with a plug seal cap. And then the tube was put inside the plastic cylinder containing water at a temperature 30 to 50 degrees Celsius. You can see. Just see the demonstration of that experiment. This is the tube coming in the cylinder. And you can see the dry ice is melting, converted into the liquid CO2. And this liquid CO2 is circulating through orange peel and extracting limonene. Yeah, so quickly we got the limonene by this. So it saves time, affordable, safe, effective, convenient. You can use the same method to extract natural products from coffee, fruits, flowers, spices. Even DST invited me to write the monograph on green chemistry experiments for UG and PG, and we have prepared this. This is non DST website. You can see this is the site, and you can download this PDF. The pharmaceutical industry is the largest waste producer industry. So we had written a book, or edited a book, and with me was the Rakesh. He is head of chemistry group and also vice president of Dr. Eddy's lab. So this book we had written for RSC, Green Chemistry Series books. And this book became so popular that I was invited to join the series advisory board to the editorial board. So just few slides, 2-3 slides, and I'm ending my lecture. This is in 2019. We have submitted an application with the University of York for organizing an international workshop on green chemistry for societal needs, healthcare, pollution, and circular economies. So we got the we became successful. Only I think 1 or 2 universities were successful in getting this grant out of the Newton Fund. So British Council awarded us this grant, and we had organized this workshop. The 25 actually participants were there from UK, and around 30 were there from uh, India. So they all attended this workshop. We have a ACS International Student chapter who is involved in green chemistry activity at University of Delhi. And our activity was, this is a very popular magazine published by American Chemical Society's Green Chemistry Institute, and they have highlighted our activities in that magazine. This is my group. These are all ACS members, and even we got an award by ACS funding to attend, my student and me, to attend the ACS national meeting at New Orleans, US. Then also one of my students got the best poster award in this conference. This is the world's best conference on green chemistry and engineering, every year organized at in US. Recently we got a green chemistry award also from ACS, our ACS student chapter, and even we were awarded global innovation grant, about 5,000 US dollar from ACS Committee on International Activities to organize a workshop. So we had organized a workshop on greening our education system, and these were the teachers and the students, participants. And lastly, I'm very happy that today I got a mail from ACS again, and they have awarded us a ACS Student Group Development and Engagement Grant Award of around 9,015 US dollar to do a green chemistry symposium series on green chemistry and sustainable development. Now, this is the last slide I'm just going to share with you. You know, whenever we take any chemical substance, anything for a reaction or a project, we always look for these properties: state of matter, color, melting point, boiling point, solubility, electrical conductivity, and the day when we will include these two also: toxicity and impact on environment. These two with these properties, that day I will stop delivering the lecture on green chemistry, because chemistry itself will be green. Thank you very much for your kind attention. Thank you.
Thank you so much, sir. I think it's a our participants have learned so many things from your valuable talk. Initially, you have discussed why green chemistry is essential for the survival of mankind. Then you discussed the harmfulness of plastic bottles and then e-waste, which is very important. We have learned many. This is the first time I personally learned this thing. And then why the importance of green chemistry for the industrial as well as in academic perspective. Then green chemistry related activities in India, and why this green activity we required to organize so many green chemistry related workshop, conference to our other industries and academy, so that industry can adapt as many as green chemistry related principles in their own industry to design drugs and other substances. Application of green chemistry in industry, like you have already mentioned, how this methyl mercaptan can be converted into DMSO because of this catalyst, and you explain the role of catalyst, and then importance of organizing green chemistry related lecture and its impact on society. Then you discuss the misuses of metals today. Today's we almost every day we are misusing and we are wasting this important metals, and then you have discussed the metal scavenging property, and you have designed a particular polymer to grab this chromium specially, and you have patented this. And then magnetic chelating polymer. Then you have discussed the application of liquid carbon dioxide to extract D-limonene specifically from orange. And then you shared so many research activities of your own from your own research based on green chemistry. So thank you so much, sir. Now I'm requesting any participants, if you have any question, you please ask sir directly, or it is a great opportunity for you people to interact. Sir he is one of the leading scientists who is working on this very fascinating area of research. So, or you can share your views. That is also important. You can share your views. So, any of the participants you want to share, express your views, please unmute yourself. Dear participants.
Sir, am I audible?
Yes, Manmeet.
Yes, sir. Yes, sir. Firstly, I want to say that the whole presentation was amazing. Yeah. Sir, am I audible?
Yeah.
Manmeet,
can hear you.
You are not audible. Any other participants? Rajvinder.
Good morning, sir.
Yes, Sivalika. Can you please unmute and share your views? Neha?
Yes, sir. Good morning, sir. Am I audible?
Yes, you are.
Good morning, sir. I'm Neha Bansal from BSc third year. Thank you for such a wonderful and nice presentation. This was very informative, and it includes many interesting things. Sir, I have actually, due to poor connection, I missed that part. That how can we use carbon dioxide as a solvent? Can you please tell me again?
I think now you have this available on YouTube also. Otherwise, I have to explain whole experiment. Or you can download this experiment from DST site.
Okay, sir. Thank you once again, sir, that you take out your time from your busy schedule and enlightening us with your knowledge. Thank you once again.
Thank you, Neha. Thank you.
Thank you, Neha. Any other participants? Because our next speaker, Professor Asish Ranjan sir also joined with us. So he is waiting. Thank you so much, sir. Thank you so much for your valuable time. Thanks a lot. And definitely, I think with your help, we can organize some workshop or conference, Green Chemistry conference at our university premises, means offline anytime when this pandemic is over. Thank you so much for. We need your help actually, and it will be great if you can help us to organize.
I'm there actually. I like popularizing green chemistry, so we will
So
do
thank you so
that.
much, sir. We are trying a little bit. I know, means very little contribution from our side.
No,
So
don't worry. So,
thank you so much. Thank you so much, sir.
thank you, Bhavan, for
Thank
inviting.
you, sir. Thank you, sir.
Thank
Now
you.
I'm like to thank you, sir. Now I'm like to invite Professor Asish Ranjan Das, sir. Sir, am I audible, sir?
Yes.
Thank you, sir. Thank you, sister. Thank you. Thanks a lot for giving us your valuable time. So, dear participants, let me introduce Professor Asish Ranjan Das, sir, for just a minute. For this, I want to share his short CV. Yes, Professor Asish Ranjan Das, sir, is a professor of organic chemistry at Department of Chemistry, University of Calcutta. Calcutta is situated at Kolkata, and he did a PhD from Jadavpur University and postdoc from 2002 to 2003 from National Tenzing University, Taiwan. Then he published more than 150 research publications, and all are in high impacted journals. And Professor Professor Das was a lecturer from 1994 to 1996 in Scottish Church College, Kolkata, and then 96 to 99 from University of Calcutta, and then senior lecturer from 99 to this 2003 in University of Calcutta, then reader from 2003 to 2006, and then associate professor from 2006 to 2011. Now he is the professor of organic chemistry from 2011 to at present. His research interests based on development of new synthetic methodologies, nanometal oxides and nanoparticles mediated catalysis, and then use of green tools and green synthetic procedures, metal ion as a promoter of carbon-carbon and carbon heteroatom bond formation, synthesis of novel heterocyclic molecules of medicinal interest. He guided more than 8 PhD scholars. I think this number is, I think it is more than 15 right now, I think, because this CV I have collected from, I think it's a backdated CV, I think. Anyway, then here's, this is the list of publications. You can see, you can collect this from the website of Calcutta University. So he has published, he has 5 patents, and this is the list of publications. So without wasting time, I am requesting you, sir. So because already 19 minutes have gone. So thank you so much once again. Thank you so much for giving us your valuable time. I think our all the participants will learn many things from your valuable lecture. Over to you, sir.
Thank you, Dr. Banerjee, for inviting me to give to give a lecture on green chemistry today. And also, I like to thank you for your nice introduction, or rather introducing me at this auspicious audience. Now, today, I have planned to talk before you green chemistry and its utility in green chemistry and its utility in organic synthesis. Before going into details, let us see some social image of chemistry. Initially, chemistry was viewed as only or sole option to achieve medicinal breakthroughs and modern conveniences. That is, chemist was engaged in promoting or rather in manufacturing or rather in preparing medicinal compounds, and also make our life very smoother so that we can live without any hazard. Unfortunately, it is now viewed as a fouling this planet. Why? Because yeah, doing chemistry experiment, you know, there is tremendous involvement of chemicals, toxic chemicals, toxic solvents, and also toxic waste. So this planet is gradually filled with so many garbages. Now the question is, what is green chemistry? Green chemistry, we can define not in a very single sentences, but its impact is very huge. But whatever may be, we can simply say that design of chemical processes, product and technologies that reduces or eliminates the use of generation of hazardous substance is the foundation of green chemistry. Or rather, if we can maintain these parameters, then then we can practice the green chemistry as well. Now, considering the aspects of green chemistry, if you look that green chemistry is the main savior of this planet. It prevents pollution at the molecular level, and green chemistry is the far beyond chemistry. It is not only restricted in the laboratory process, but also a great philosophy that applies to all areas of chemistry, not a single discipline of chemistry. And also this particular green chemistry applies innovative scientific solutions to real world to solve environmental problems. Results in source reduction doing or practicing green chemistry, because it prevents the generation of pollution. And also it reduces the negative impacts of chemical products and processes on human health and the environment. Moreover, lessons and sometimes eliminates hazards from existing products and processes, also the great area of green chemistry. And also finally, designs chemical products and processes to reduce their intrinsic hazards. Now, as I have mentioned that green chemistry has severe impact on the laboratory processes, designing chemical reaction and in materializing that particular chemical reaction in the laboratory. So green chemistry has a very profound or definite role for cleaning up pollution. What is that? Now, green chemistry reduces pollution at its source by minimizing or eliminating the hazards of chemical feedstocks, reagents, solvents, and products. That is, when we are designing chemical reaction in our laboratory or in the industry, whatever may be the place, but we have to keep in mind that there should be least hazard or involvement of least hazardous solvents, reagents, and also the product that will arise, main product or our desired product or the target molecule along with the side product that will create minimum pollution to the environment. Now already we know that scientists across the global have developed 12 design principles of green chemistry. I think all of you know this particular 12 design principles, but at this stage, if I mention it again, then you can recall or recapitulate it. Number one is the prevention of waste rather than the cleaning up the waste after it has been created. Rather, not to clean the waste after the reaction or the experiment is over, but if we can prevent the waste generation, that would be better in the context of green chemistry. Atomic economy is a very big problem in chemistry or in chemical science or in material science as well. We have to very careful so that number of molecules at the reactant level that will react undergoing reaction to generate the product where the atom economy will be maintained, highly maintained. That is, atom economy in the synthetic method should be designed so that maximize incorporation of all materials used in the process into the final product. If that be the case, then there should be minimum generation of or no waste generation after the reaction is over. And number three is the less hazardous chemical synthesis. Wherever practical, we should try the synthetic methods so that use and generation of substances that poses little or no toxicity to human health and also to the environment. Number four is the designing safer chemicals. Chemical products should be designed to preserve efficacy of function while reducing toxicity. That is, chemical products should be developed in that way, or rather it has to be preserved in that way that it has no function or it will create no toxicity. Rather, the toxicity in general will be reduced during generation of the product. Number five is the safer solvents and auxiliaries. The use of auxiliary substances, for example, solvents, separating agents, etc., should be made unnecessary. Carrying out simple experiment. After that, if it is become possible to purify that particular product without the involvement of chromatography, that is use of silica gel, solvent, etc., other if it can be purified by a simple crystallization method, that would be better in the perspective of green chemistry. Design for energy efficiency also a very important part of green chemistry, because energy requirements should be recognized for their environmental and economic impacts and should be minimized. Synthetic methods should be conducted at ambient temperature and pressure. Unnecessary or rather avoid of very high temperature and very high pressure in carrying out experiment should be avoided, so that no extra imposition in the reaction vessel should be imposed so that there is the possibility of generating more byproducts. Number 7 is the use of renewable feedstocks. A raw material or feedstock should be renewable rather than depleting whenever technically and economically practicable. Number 8 is the reduced derivatives, unnecessary derivatization, rather use of blocking groups, protection, deprotection, temporary modification of physical and chemical processes should be minimized or avoided if possible, because such steps require additional reagents and can generate waste. In a particular targeted synthesis, if we can achieve that particular synthesis in a very short method, or rather involving many minimum steps, then it would be far much more better rather than the involvement of more steps. Catalysis is also a very big part in synthetic chemistry. Catalytic reagents, as selective as possible, are superior to stoichiometric reagents, because we know that catalysis can accelerate a particular reaction, and its role in the chemical reaction is to use in catalytic amount. There obviously there should be some optimum concentration, as required from its reaction rate, but always in most of the cases the catalysis that is required is the catalytic amount instead of stoichiometric amount, and that is better in terms of cost and also in terms of toxicity. And number 10 is the design for degradation. This particular term should be explained that the chemical products should be designed so that at the end of their function, they break down into innocuous degradation products and do not persist in the environment. That is chemical reagents and that are being employed to carry out a particular reaction are designed in such a way after the reaction is over, so that it may, after reaction, it may breaks down into very smaller fragments, so that it has very little impact or rather no impact in the environment. And we have to analyze during the chemical reaction process is the real-time analysis for pollution prevention. Analytical methodologies need to be further developed to allow for real-time in-process monitoring and control prior to the formation of hazardous substances. And finally, inherently safer chemistry for accident prevention is also a very safer part for green chemistry, because substances and the form of a substance used in a chemical process should be chosen to minimize the potential for chemical accidents, including releases, explosions, and fires. That chemical should be avoided in carrying out very smoother and greener chemical reactions. Now, green chemistry in organic synthesis, if we look how green chemistry can be employed so as to get very clean with no pollution or rather minimum pollution, which is the basic requirement of the green chemistry, can be carried out. First, I like to give you one particular example already established. This is the boot process for the synthesis of ibuprofen. This is a very good anti-analgesic drug, and not anti-analgesic, but analgesic drug. Is basically a painkiller. And for this very purpose, Boot had chosen this particular compound starting from isobutyl benzene, acetylation in presence of aluminium chloride, the corresponding acetyl group enters into the position number 4. And during this particular process, this particular environment acquires some sort of chemical waste, which is nothing but hydrochloric acid, acetic acid, and aluminium containing salt as the waste. Now, after that, after incorporating acetyl group at the position number 4 of isobutyl benzene, if you carry out Darjeeling's glycidic acid ester condensation, taking ethyl chloroacetate in presence of sodium ethoxide as base, and during that particular process, the corresponding epoxide has been generated. That is, carbonyl group reacts with the alpha chloroacetate, generating this particular epoxide, but has been shown in this particular slide. Now, during this particular process, a high amount of HCl is being evaluated during this particular process. It may go outside if the basicity of the reaction medium is optimal, then HCl will go out in the form of gas and it will go into the air, or rather the corresponding surrounding will be polluted. Next, when this particular epoxide is being hydrolyzed, then it will generate the aldehyde functionality along with the in its alpha position there contains a methyl. And during this particular process, the OST is nothing but the correspondingly only acetic acid. And during oxygen generation or protection of this particular aldehyde functionality to hydroxylamine, this is very safer chemical reaction. And after that, if we dehydrate this particular oxygen to generate C111N, that is the nitrile functionality, we have to carry out, or we have to place some adsorbent, so that that can, on heating, that can absorb the water molecule, and elimination can take place, leading to the generation of C111N functionality. And after that, hydrolysis, again acid catalyzed hydrolysis obviously will generate the corresponding carboxylic acid, or rather the target molecule of brufen, and during this particular process ammonia will be generated and it may go out to the environment. So this particular method what Boot has suggested for the synthesis of brufen is not very very facile or very safer, but in the perspective of green chemistry. Rather, if you look the haste process for the synthesis of ibuprofen, it is very greener route for attaining the synthesis of the corresponding ibuprofen. First, taking from isobutyl benzene, if we carry out acetylation in presence of HF as the gas, then acetyl group will be incorporated into the para position. Reduction by means of molecular hydrogen, placing nickel, finely powdered nickel as the catalyst, it will generate the secondary alcohol. And after that, it has become possible with the help of palladium catalyst in insertion of carbon monoxide to the oxygen and carbon bond to generate the carboxylic acid. And during this particular process, the steps involved is 3 minimum steps. Not only that, minimum waste are coming out after every step or after each step. So from that particular green chemistry point of view, this particular haste process is superior in the context of green chemistry when compared to the Wood process. Now, in second example, Woodward cis hydroxylation, if we see that cis olefin can be hydroxylated by means of Woodward process, Woodward-Woodward hydroxylation method, by employing iodine and silver acetate acetic acid water, so that one hydroxyl group after generation will be protected by making its acetyl derivative, which on hydrolysis will generate the corresponding cis diol. And if we consider this particular process, Upjohn dihydroxylation method, which involves the olefinic compound when treated with catalytic amount of that is very minute quantity of osmium tetroxide in presence of N-methyl morpholine N oxide and water, then it will generate in turn generate the corresponding cis diol. From this particular correlation of the Woodward pivot hydroxylation method and the Upjohn dihydroxylation method, if we consider both the process, then we will see or we can recommend that Upjohn process is the greener in comparison to Woodward pivot hydroxylation method. Now, with this particular preview or rather introduction, I like to present before you what we are doing during the last 4 or 5 years, taking green chemistry as the tool or employing green chemistry principles in organic synthesis, so that easily we can easily achieve very biologically relevant molecule or some bioactive molecules. First, we have planned to carry out solvent-based reaction. In the first case, I am citing the solvent-based reaction. In this particular case, we have carried out copper iodide zinc acetate combo catalyzed approach for making CsP2H activation for the synthesis of pyridocoumarins using solvent-free ball milling approach. Now, for this very purpose, in order to carry out this particular reaction, we have substituted 3 aminocoumarins. We have taken the corresponding aldehyde, aromatic aldehyde, or heteroaryl aldehyde, whatever may be, and also carbonyl acetylene as a starting precursor. And these 3 particular components in presence of P+ iodide and zinc acetate under ball milling. And ball milling condition is the high vibrational ball milling carried out, high ball milling apparatus, and grinded at 30 Hertz, frequency is 30 Hertz. And solvent free, if we carry out this particular reaction, then within 35 to 90 minutes, it is possible to get the access of the corresponding pyridocoumarin derivative. Now, in this particular case, we have seen that already we have in the starting material 3 aminocoumarin, the corresponding benzene ring is being substituted by either halogen or methoxy substituted, that has been retained in this particular product, and also another substituent that has been come from this particular aldehyde part, so that it leads to the subsequence at the pyridine ring, at the 2 position of the pyridine ring, and finally in pyridine ring also there is the presence of, in number 4, there is the presence of aromatic ring which comes from the acetylenic part. Now, going into details of this particular reaction, if we like to investigate the inside of this particular chemical reaction or possible mechanism of this reaction, then we will see that this particular hydrogen, CsP2A hydrogen, is being activated, and also not only that, in this particular case 2-CC coupling reaction has been achieved. Not only that, another carbon nitrogen coupling also been carried out, so that ultimately this particular reaction indicates the formation of 2-CC coupling reaction and 1 carbon nitrogen coupling reaction. That is carrying out single operation. Simultaneously, it involves 3 sequential steps, 2-CC coupling and 1 CN coupling, leading to the formation of this particular pyridocoumarine derivatives under solventless reaction condition. Now, if we look very detailed in this particular reaction mechanism, then acetylene first forms the corresponding copper acetylide, and 3-aminocoumarine and aldehyde generates this particular N alkyl substituted aminocoumarines, which in presence of P plus iodide forms this particular intermediate copper 3 complex, that is copper 1 is being switched to copper 3 complex, and zinc acetate, or rather zinc plus 2, activates the reaction between 3-aminocoumarine and aldehyde, and after that CC coupling will take place, and finally deductive elimination of P plus iodide. This particular cycle will be continued. So it is possible after completion of this particular cycle, the reaction loses its equilibrium and finally go on to the product side. And eventually it is possible to get the very high degree yield of the particular process. So from this particular green chemistry point of view, this particular reaction, after this particular reaction, the product that has been arised can be easily purified by carrying out simple crystallization technique. So avoidance of this chromatographic technique can also be carried out. The involvement of huge solvent as a feedstock can also be avoided in this particular case. Now, second reaction that I will cite is another involvement of magnetically separable heterogeneous catalyst, so that involvement preparing this particular magnetically separated heterogeneous catalyst. In this particular case, I will cite that is nanocrystalline nickel ferrite. We have able to synthesize it under and this particular catalyst is highly stable even under aerobic condition, that is in presence of oxygen. And also this particular catalyst has the another feature, that is it does not require any ligand, and so that organic chemists can carry out carbon nitrogen bond formation, carbon oxygen bond formation, and carbon carbon cross coupling reaction as well. And if we look the schematic presentation of this particular reaction, then aryl and heteroaryl halide in presence of some nucleophile, placing cesium carbonate as base, dioxane as the solvent under refluxing condition, and nickel ferrite as the magnetically separable catalyst under ligand-free condition. It will generate this particular product, that is the carbon nitrogen, carbon oxygen, and carbon carbon cross coupling product. The comparable catalytic efficiency is being achieved with respect to traditional palladium and copper catalyst is a very salient feature of this particular developed catalyst. Excellent product yield and easily recoverable catalytic system is very handy for the students to carry out this particular reaction. Now, if we look the substrate scope, then a different carbon nitrogen coupling reaction can be carried out, different carbon oxygen coupling reaction can be carried out, different carbon carbon coupling reaction, that is that also be carried out employing this particular catalyst. And possible mechanism in this particular case is very simple. Initially aryl halide undergoes oxidative addition across the magnetically separable catalyst, so that catalyst and the aryl halide attack has been generated. After that, in presence of cesium carbonate and nucleophile, it undergoes leaving group exchange reaction, that is halide ion is being eliminated and the nucleophile is being incorporated into the catalytic site of this catalyst or surface of the catalyst, and after that reductive elimination leads to the generation of ARNU as the product and together with the generation of this particular catalyst. And in this particular case, we have employed the nickel ferrite as a nano catalyst, and nucleophile is aryl heteroaryl amine, the corresponding phenol and the corresponding boronic acid. And X in this particular case, what we have represented here is aryl halide. It can be iodide bromide chloride or it can be boronic acid. That is, the salient feature is that in this particular case, boronic acid can act as electrophile, can act as nucleophile as well in the presence of this particular catalytic system. Now, switching our attention from nano nickel ferrite to nano copper ferrite, this particular catalyst already established. So many scientists have been able to carry out so many chemical reactions. Now we have designed, in this particular case, copper ferrite, nano copper ferrite is being taken, and instead of 3 aminocoumarin, if we take 4 aminocoumarin or 4 substituted aminocoumarins and glyoxal as the 1,2-dicarbonyl precursor and amine as the base and also the nucleophile, then employing nano copper ferrite 10 mole% and carrying out the reaction not in any organic solvent but placing pure water as the solvent and carry out the reaction at 70 degrees centigrade, it is possible to get the excess of pyrrolochromines or rather coumarin substituted pyrrole derivative. And in this particular case, if we look this particular chemical reaction, this is purely green in character. That is, we have designed this particular reaction maintaining extremely green protocol, and obviously in this particular case we have allowed 10 per mole% of the nano copper ferrite as the catalyst, and that particular nano catalyst can be separated after the reaction is over and got its identity back. At least 10 cycles, 10 reactions can be carried out by taking this particular originally taken catalyst without not full catalytic activity has been retained, but 10 to 20% catalytic activity has been reduced because this is due to the leaching of this particular nano catalyst. So in this particular case, it is being possible to generate chromino-4,3-B pyrrole 4,1H1, that is this particular chromino-pyrrole system. And possible mechanism of this particular reaction is very simple. This particular amine is reacting with aldehyde to generate the imine first, and this particular imine will be polarized in presence of copper +2 present in the copper ferrite system, and that will suffer nucleophilic attack by the alpha position of the 4 aminocoumarin, and then it will generate this particular 1, 2, 3, 4, 5, 1, 5 dipolarophilic species. It will undergo equilibration reaction to generate the corresponding enamine and the corresponding carbonyl, which being polarized by the iron +3 center undergoes cyclization to generate the corresponding chromino-pyrrole derivative. So very high degree of yield and very smooth reaction can be carried out. No need of very skilled hand to carry out this particular reaction. That is also a very good approach for the practicing green chemistry. And also we have developed extremely column chromatography reaction in aqueous medium that has been developed early in this decade. In 2011, we have planned to synthesize this particular compound by placing 3-hydroxycoumarin, malonitrile, and aromatic aldehyde in presence of nano zinc oxide as the catalyst, water as the solvent at 70 degrees centigrade, and under that particular condition, dihydropyranochromine system has been developed with the aid of 3-hydroxychloroquine. This is also this particular reaction has also been considered as the green synthesis because water has been employed as the solvent, nano zinc oxide has been applied as a catalyst. Mild, very mild reaction condition, 70 degrees centigrade is the most optimum temperature of this particular reaction system, and easily separable nano zinc oxide. That is, zinc oxide can be separated by simple filtration technique. And reaction mechanistic side or inside of this particular chemical reaction involves the formation of this particular Neuvenagel attack first, and then it will suffer nucleophilic or the corresponding Michael type of addition from 3-hydroxycoumarin, where the corresponding 1,2-dipolarophilic species, that is the dicarbonyl derivable by the enolization of 3-hydroxycoumarin, or rather ketoenol tautomerization of the 3-hydroxycoumarin, the 1,2-diketone has been stabilized by nano zinc oxide, and also both the electrophilic center cyanide, the dipolarophilic character, repulsion of dipolarophile is being minimized by the involvement of the nano zinc oxide, and finally it leads to the development of this particular pyranochromin derivative. Next is the synthesis of benzyl pyrazolyl coumarin derivatives by a 4-component reaction in water medium. We have designed 4-component chemical reaction placing 4-hydroxycoumarin, aromatic aldehyde, beta-keto ester, or hydrogen or its derivative, aromatic derivative or aliphatic derivative. And in that particular case, it is being possible to design column chromatography 3, placing water as the reaction medium, this particular benzyl pyrazolyl coumarin derivative. And this particular compound is very interesting from the crystallographic point of view, and also from medicinal point of view, because both coumarin and pyrazole ring has the bactericidal activity, and it is being possible to generate at least 15 examples for to produce this type of pyranochromin derivatives. And the structure has been solved by placing crystallographic techniques, by rather by generating single crystal compound. And in this particular case, mechanism is very simple. This first hydrogen reacts with beta-keto ester, generates the corresponding pyrazolone derivative, and 4-hydroxycoumarin reacts with aromatic aldehyde to generate the quinone methionide, and quinone methionide suffers nucleophilic attack from the pyrazolone, and after that, proton elimination, dehydration, etc., leads to the generation of the compound 5, that is the target molecule. So a very, it's a different kind of reaction. First is the condensation reaction, so to undergo cyclization or form a cycle, then condensation reaction, then Michael addition reaction, and finally ketoenol tautomerization has been carried out without the involvement of any acid or base. Rather, the substrates, rather the reagents, rather the chemicals involved during this particular process are sufficient or are sufficiently potent to control, or rather to drive the equilibrium of this particular reaction towards the product side. And use of green solvents other than water, we have also been able to choice, or rather able to establish lactic acid as the green acid catalyst, and ethyl lactate as the green solvent for the generation of this type of indeno dihydropyridyl and dihydropyridyl system. That is, in this particular case, 4-aminocoumarin, aromatic aldehyde, and the corresponding indene 1,3-dione is being reacted to generate the corresponding indeno dihydropyridyl system, and 4-aminocoumarin, aromatic aldehyde, and dimidone. In this particular case, the indeno dihydropyridyl system has coumarino dihydropyridyl system has been synthesized very successfully, placing ethyl lactate as green solvent and lactic acid as cost-effective and less hazardous catalyst. We know that lactic acid can can be achievable from the nature. Many of the lemon contains the corresponding lactic acid. And so by placing green acid catalyst and green solvent, it is possible for the 3-component coupling reaction, generating a very a linearly fused 1, 2, 3, 4, 5-membered ring and 1, 2, 3, 4, 4-membered ring in the form of dihydropyridyl system. And this particular dihydropyridyl system can also oxidize to generate the corresponding pyridine ring if we can oxidize this particular compound with DDQ in dichloromethane as a solvent. And in this particular case, mechanism is very simple. First, once the dicarbonyl reacts with aldehyde to generate the corresponding double bond or the corresponding condensation product, and then coumarin attacks this particular Neuvenagel attack by maintaining 1 pore addition sequence, and finally condensation of amine and the carbonyl generates the corresponding dihydropyridyl system. And during this particular reaction, we have used some metal catalyst, some acid catalyst, and placing no catalyst, that is only water as the reaction medium. That also we have been able to carry out or design some chemical reaction or chemical operation. Now, in this particular case, we are highly interested to carry out some acid catalyzed reaction, placing no metal, no Lewis acid, no direct acid catalyst, but we have been able to prepare polyethylene glycol sulfonated acid catalyst that has been derivable from polyethylene glycol. I will show you how this particular compound has been developed by our research group. In this particular reaction, the reaction has been designed in this way, that is either 3-hydroxycoumarin or 4-hydroxycoumarin. That 1,3-dicarbonyl compound containing material, that is 1,3-cyclohexane 1,3-dione or dimidone, is being reacted with malonyl, and to this, if we add this aromatic aldehyde, then it is possible to achieve this corresponding dihydropyran derivative, which contains in dihydropyran in its 2 position amino group and 3 position the corresponding cyano group. So this particular reaction is being carried out in presence of organic solvent and at 70 degrees centigrade, so that it is become possible to get the corresponding substituted pyrano-coumarin derivative. Now, starting from polyethylene glycol, in order to prepare the corresponding PEG-SAC catalyst, first polyethylene glycol is being sulfonated by the presence of chlorosulfonic acid as the acid catalyst and the corresponding secondary amine as the base, and to this it is being generated the corresponding sulfonate ester. And this sulfonated ester under pyrolytic condition 400 to 500 degrees centigrade and incomplete carbonization leads to the development of PEG-SAC catalyst. The corresponding structure has been developed by carrying out same powdered XRD method. And also the beauty of this particular solid or polymeric acid catalyst is that sulfonic acid is become active and all are the corresponding carbon chain. No other catalyst is being present to this particular reaction system, and it is powder in category, so the surface area becomes very high. So substrate scope in this particular case also, this the total 31 compounds we have been able to synthesize up to maximum yield of 96%, and structural motif has been established by carrying out single crystal X-ray crystallography. Now, after this, we are also able to develop a particular chemical reaction in which solvent mediated. Solvent means in this particular case, we have designed the solvent as the water, and without any solvent, we can direct one particular reaction in a definite direction. Say, for example, if we have this particular primary amine and aldehyde as the catalyst, aldehyde as the another reagent, aromatic aldehyde, and diethyl propionate is the another reactant, then placing graphene oxide nanosheets water at room temperature near about 50 to 80 minutes without heating photochemical condition or any or in presence of any photocatalyzed light, photoactive light, that it undergoes cyclization reaction to generate the corresponding 2-pyrrolidone system. And achieving this particular 2-pyrrolidone molecule, if we replace the water as the solvent, then if we carry out the same reaction in presence of same reactant, same acid, same catalyst, graphene oxide nanosheet, at room temperature, employing same reaction time, then it is possible to get the corresponding 2-furanone derivative. And instead of water, instead of solvent-free, if we add to this another amine as the reactant, then it undergoes further chemical reaction to generate the corresponding again 2-pyrrolidone derivative. But this particular pyrrolidone is different from initially achieved 2-pyrrolidone molecule. In that particular case, there is the presence of 3-hydroxy functionality. In this particular case, this amino-alkyl or alkyl amino functionality. So in this particular case, we have been able to unravel the solvent selectivity, that in presence of solvent, it generates the corresponding 2-pyrrolidone molecule, and in absence of solvent, it generates the corresponding 2-pyridone as a molecule. And on water and solvent-free condition, both have been developed very successfully, and also employed graphene oxide, that is carbon-based nanomaterial, as the catalyst. So this is the chemical reaction or schematic presentation of these 3 different reactions. In this particular case, we have been able to prepare at least 37 compounds by employing this particular chemical manipulation. Now, plausible mechanism of this particular reaction is that in water, this particular aldehyde is being activated, or this particular oxygen is being coordinated with the carboxylic acid presence in the graphene oxide, so that this particular carbonyl center is being polarized, other electropositivity becomes, or electrophilicity becomes increased. It will suffer a nucleophilic attack from the secondary amine to generate the corresponding imine compound, and that particular imine compound on reaction again polarized by the corresponding carboxylic acid of the graphene oxide. And in this particular case, the corresponding ethyl propiolate undergoes acid catalyzed hydrolysis because graphene is being present, graphene oxide is being present, it contains acid functionality. In presence of water, it will undergo acidolysis, and it will undergo this carbon-carbon triple bond, undergo addition of water molecule, so that this particular compound is being generated. This will behave like Michael donor. It will attack at this particular Michael acceptor to generate this particular 1, 2, 3, 4, 5 atom containing chain length molecule, and in alpha end it contains the carbonyl functionality, and omega end it contains the nucleophilic amine functionality. It then again attacks to generate the corresponding after ethanol elimination, it generates corresponding 2-pyrrolidone molecule. And under solvent-free condition, this particular ethyl propiolate initial undergoes hydroamination reaction, because in this particular case, it does not undergo hydrolysis because of the avoid of water as the solvent, rather it follows hydroamination reaction to generate the enamine, and that enamine will attack the carbonyl compound to generate this particular adduct, or this particular enamine may react with aldehyde to generate this type of adduct, which on cyclization generates 2-furanone derivative. Even that, if enamine reacts with aldehyde in this particular fashion from the beta side, then also it undergoes elimination, addition reaction or nucleophilic attack, then undergoes U1CB elimination. U1CB elimination to generate the conjugated imine system, and that particular imine suffers nucleophilic operation or nucleophilic attack by the externally applied amine, and finally it leads to the development of the corresponding 3 amino alkyl substituted to 2-pyrrolidone molecule. And in this particular case, 2-furanone is the outcome of this particular reaction. So in this particular case, it was possible to us to unravel the solvent activity. What is actually the role of water as the solvent, and in absence of water and in presence of water, how the reaction participates in the different mode. It is also it is also possible to us to solve the or to find out the exact pathway when water is present and when water is absent. And finally, it is possible to us to develop a variety of the corresponding different compounds, 3 types of compounds. And finally, within the last 2 slides, I will show you how employing green organocatalyst for intermolecular can be utilized in achieving intramolecular rearrangement. For the preparation of pyrano-oxazolone system, we have prepared this particular compound very easily by the starting from the 2-amino-3-cyanodihydropyran molecule in presence of iodobenzene diacetate and the corresponding iodosyl benzene as the acid catalyst, as the Lewis acid catalyst. And after that, taking this particular compound, if you treat this particular molecule with tetrabutyl ammonium fluoride in dioxane as the solvent, it undergoes smooth molecular rearrangement, and eventually it is being converted into the corresponding pyrano-oxazolone. And this particular molecular rearrangement is very interesting. Look, this inside of this particular reaction, this particular molecule is like this. Tetrabutyl ammonium fluoride first abstract the hydrogen over nitrogen to generate the nitrogen center anion, which is becomes anionic, becomes the nucleophilic in origin. It will attack the corresponding acetyl site, and initially when the acetyl N minus is attacking acetyl part, the oxygen non-bonding electron moves to support this, and eventually this 3-member nitrogen being open up, and eventually this is the possible orientation of the molecule so that N minus can attack at the acetyl site from the beta position. And after that, when O minus and when this N minus attack at this particular carbonate will assume the corresponding alkoxide. And when this alkoxide backs, the R group, which is bonding pair of electron, migrates from the top side, and eventually R and E bear the same relationship. Initially, it was both the substituents alpha. Now both the substituent is beta. So intermolecular rearrangement, not only intermolecular rearrangement, but very regioselective rearrangement and very diastereoselective synthesis can be carried out during the synthesis of pyrano-oxazolone from dihydropyran, 2-amino-3-cyanopyran molecule. So employing tetrabutyl ammonium fluoride and dioxane as the solvent, it is now become possible for the employing green organocatalyst to achieve the smooth, very smooth molecular rearrangement. The synthesis of pyrano-oxazolone. These are the very representative pyrano-oxazolone molecule, the structure of which has been established by single crystal X-ray crystallography. So by carrying out this particular green chemistry technique, it has become possible for us to synthesize this type of fused pyrano-oxazolone molecule. Next is the involvement of paratoluene sulfonic acid as the green acid catalyst and alcohol as the solvent, taken the same agilidine molecule, pyranoagilidine molecule. It is now possible to us to convert this particular pyranoagilidine molecule, or rather for dihydropyranoagilidine molecule, to convert this in presence of paratoluene sulfonic acid and alcohol as the solvent. It is now possible to get the access of pyrrole derivative or substituted pyrrole derivative. In this particular case also, a molecular rearrangement is being operated so that in this particular case, it is also become possible to get the access of the corresponding cyanide, and this particular phenyl ring is being the syn relationships, and this particular dihydropyrrole system is being generated. And also not only that, a particularly interesting feature is that alpha to nitrogen center in the pyrrole ring is the quaternary one, and also the 3 position is a tertiary one. So at least one particular another important manifestation by carrying out this particular reaction is that generation of quaternary center becomes possible, and also a substituent like aromatic ring is placement is become possible at the position number 3. So a substituted pyrrole ring containing highly substituted, when a tri-substituted pyrrole ring is being generation becomes possible by carrying out this particular reaction. And mechanism in this particular case is also very simple. Initially, the corresponding aziridine undergoes cleavage by taking the corresponding proton from parasolvent sulfonic acid in alcohol as the solvent, and after that, when this particular bond is opened up, the corresponding alcohol attacks at this particular center, so that acetyl group also eliminated, and this particular center becomes the ketal one. And when this particular center assumes the ketal one, this particular amine center can attack at this particular ketal center, which is highly electrophilic one because of the presence of 3 withdrawing effect of the oxygen. So in this center is highly electrophilic one. So this particular nucleophilic amine will attack at this center, and the ring will be opened up. And after that, hydrolytic sequence and also bond rotation allows this particular amine and this particular carbonyl to come closer, so that the orientation of the E group already present in this molecule and the corresponding ester group bears the anti-relationships, and E group assumes the syn relationships with this particular alkyl group, which is being placed at the position number 3. And after the cyclization of amine and alpha N and omega N carbonyl leads to the generation of pyrrole derivative. And during that particular process, the position number 2 becomes the tertiary one, and position number 4 becomes the quaternary one, and position number 3 is the tertiary one. So a substituted pyrrole derivative can be realized by placing mild organic acid catalyst or other green acid catalyzed condition and alcohol as the solvent. So if I sum up our synthetic groups achieved applying during green chemistry is the multi-component reaction, carbon-carbon bond formation reaction, carbon-nitrogen bond formation reaction, and carbon-oxygen bond formation reaction. In addition, we are also able to get some intermolecular rearrangement so that fused heterocycline can also be synthesized. And finally, I am very much acknowledged to my students who are engaged in this particular process for a very long time. This is Dr. Sanjay Paul. This is Dr. Parthapotin Ghosh, this is Dr. Koel Pradhan, Dr. Prasun Mukherjee, Dr. Najia Kaushar, and this is Mohamita Shah. All got PhD degree from my laboratory, and she is about to submit her thesis. Prasun is doing postdoc in Professor Maiti's lab, Professor Devbroto Maiti's lab in IIT Bombay, and all 4 students are in the teaching profession. So I am very thankful to all of them by their sincere work. Without their sincere work, it was not possible for our laboratory to develop such a very skilled green chemistry techniques. And finally, I thank you for your kind attention and also patience. Finally, I thank you all.
Thank you so much, sir, for your very valuable talk. I think our participants have learned many things, learned many synthetic routes, synthetic procedures for the synthesis of various biologically active scaffolds, and you have utilized in many maximum cases, not maximum in all cases, I think. Various green chemistry principles you have utilized this, like multi-component reactions, use of metal, in some cases use of non-metal, metal-free organocatalysis, green solvents, room temperature reactions, and in as it's multi-component reaction, that means it's atom economy. So you have all explained in your introductory lecture. You have explained the importance of green chemistry, and you have explained all the 12 principles in very detail. And then you have showed the greener route of ibuprofen and why this green chemistry is important. Then you have discussed by a ball milling approach for the synthesis of pyridobromine synthesis, and then use of magnetically separable heterogeneous catalyst. And you have designed a particular specific method using magnetically nickel ferrite or copper ferrite. You have applied all those catalysts for the synthesis of various biological active scaffolds. Then Promino 3,4-D pyrrolo 4-1H phone. This is also a biologically active scaffold. Then specifically column chromatography free reactions. That is very important because in a reaction we may use 1 ml or 2 ml solvent, but during column chromatography almost 1 liter or in some cases 2 liter petroleum ether or ethyl acetate is required. So if you can avoid this column chromatography, that is very good, because during reaction it may be 1 or 2 ml solvents are used, but during column chromatography separation liters of solvents are required for the purification. So if we can design a process so that we can avoid column chromatography, that is very good. And by using column chromatography techniques, you have synthesized dihydropyridino 2,3 chromines using nano zinc oxide, then benzyl pyrazolochromine, and then by using lactic acid as catalyst in ethyl L-lactate as the medium, and you have synthesized indeno-fused pyridyls, and then PEG sulfonic acid catalyzed various pyran derivatives, and then graphene oxide nano seeds. By using this as a catalyst, you have synthesized 3,4,5 trisubstituted furan under solvent and under solvent-free condition, and you have achieved various different products in water and under solvent-free condition by using various amines. And then you have showed the synthesis of this pyrano-oxazolone and the synthesis of pyrrole using paratoluene sulfonic acid. So thank you so much, sir, and you have explained all the reactions, and you have explained the plausible mechanism involved in all the steps. Thank you so much. And sir, I have personally, I have one query. Like in this benzyl pyrazolone coumarin, during this benzylo-pyrazolo coumarin synthesis, there is no bis coumaral was formed.
No, under this particular condition, no bis coumarin is formed.
Okay, but otherwise in other catalysts, by using other catalysts, I personally have checked this when I tried to incorporate other substance.
In this particular case, we have placed zinc oxide.
Okay.
Instead of if the catalyst or the water medium is slightly acidic in nature, there is the formation of bis coumarin.
Okay, okay.
Since zinc oxide is an amphoteric, so yes, pH is almost 7, almost or slightly higher than 7.
Okay, that is very good, sir, because I faced this problem during when I tried this type of reaction. And another one is, sir, 3-amino coumarin. Have you purchased it or you have prepared this?
We are preparing. Every time we are preparing it.
Okay, means it is available in the literature, the preparation.
Yeah.
Okay, means this.
I will give you the preparation.
Okay, thank you, sir. This 3-amino as well as this 4-amino.
Okay, no problem. We are preparing every time in our lab because purchase cost much amount.
Yes, ma'am. That's why I'm asking, because this is the I think in already this is a very costly chemical. Thank you so much, sir. Thank you for your very nice lecture. Now I'm requesting any participants, if you have any question or queries, or you can share your views, because this is a great opportunity for you people to interact directly with sir. So any participants want to share your views, please unmute yourself. Yes, Aditi, can you please unmute and share your views? Neha? Neha, can you please unmute and share your views? Manpreet, there is some technical problem. Any participants?
I think they are feeling shaky. If they have any question, they can directly mail me. I will give them answer. Okay.
Okay,
No
sir.
problem.
Okay. Thank you, sir.
Okay. Thank you also for inviting
Thank you.
me.
Now I'm requesting Professor Dr. Sandeep Kumar sir, our HOD, for the valedictory. Please share some words for the valedictory function of this first session.
Actually, I got a message from our participant that they were not able to unmute themselves. So I request my Kali University host, Sunilji, if you can listen, please give permission to unmute the participants.
Hello, good afternoon, sir. This side Aditi. Actually, there is some problem. It's not mic is not getting unmuted now. That's why I'm not able to speak at time. Good afternoon to everyone. Am I audible to everyone?
Yes.
Okay. First of all, thank you so much, sir, for sharing your work. And literally, this inspire us for towards green chemistry and green catalyst and multi-component reactions, and especially towards green chemistry in organic synthesis. And it's my privilege to interact with you. And I personally learned so many things, and I'm very grateful that I'm able to attend your lecture. Thank you so much, sir, for your time and for your efforts. Thank you so much, sir.
Thank you. Thank you also.
Thank you, Aditi. Now, any other participants? Neha?
Yes, sir. Good afternoon, sir.
Good
Thank you
afternoon.
so much, sir, for such a wonderful and nice presentation. This was very much full of knowledge, and we learned many interesting things from it, especially when you told about lactic acid mediated synthesis and column chromatography. Thank you so much, sir, once again.
Thank you also.
Thank you, Neha. Now, any other participants wants to share your views? So, if not, then I am requesting Dr. Sandeep, please say a few words as a vote of thanks for this session.
Thank you, Dr. Budhan. It's my great privilege to extend my gratitude to such a revered personalities, Dr. R.K. Sharma sir and Asish sir. Their lecture, their delivery, their way of presentation was excellent, way beyond excellent, and their work is really good. And hopefully, this these great minds which are building their careers in chemistry, they will get a definitely good knowledge about the subject, especially green chemistry, and definitely they will. This topic will help in uh, increasing their knowledge. I especially thanks. I want to extend my thanks to R.K. Sharma sir and Ashish Ranjan sir for sparing their valuable time for our participants, our students, and they learned a lot from you. And in future, if we get chance to interact you face to face, uh, sorry, sorry. In future, if we get a chance to interact with you, and we'll definitely invite you for personal interaction with those students. Thank you, sir. Thank you for your great knowledgeable presentation. Thank you, Ashish Ranita, sir. Thank you very much. Govind, sir.
Thank you.
Yes, thank you so much, sir, Dr. Sandeep. Yeah, Musara, do you want to say something? because you have message, or Dr. Nasib Singh. Okay, so thank you so much, sir. Once again, thank you, Asish sir, for your valuable time. Thank you so much. Now, dear participants, we'll again meet at 1:45 p.m. for the next session of today's webinar. The speaker will be Professor Anil Kumar Gopinathan sir and Basudeb Basu sir. So thank you so much. Thank you again, Asish Ranjan Das sir, and thanks to all participants. Thanks a lot. Very good afternoon, Dr. Anil, Professor Anil Kumar Gopinathan, sir. Can you hear me? Am I audible?
Yeah, I can hear you. Can you hear me?
Yes, yes, sir.
Okay.
Thank you so much, sir. Thank you so much for giving this opportunity for our students to hear you. So, sir, we will start sharp at 2 p.m. Let all the participants to enter. Okay, sir.
Yeah, sure.
Thank you, sir. Sir, we will start sharp at 2.
Okay.
Thank you. So very good afternoon to all the participants and respected speaker, Professor Anil Kumar Gopinathan sir. Thank you so much once again as you have agreed to deliver your valuable talk for our participants. So to welcome you, to welcome Professor Gopinathan, I want to share his short CV. Just a minute. So, dear participants, Professor Gopinathan is a full professor of organic chemistry, School of Chemical Science, Mahatma Gandhi University, it's Kottayam, Kerala, and Professor Gopinathan did his PhD in 1996 from University of Kerala under the supervision of Professor Vijay Nair sir, and he did after that, and I must mention here. Professor Gopinathan secured the first position, first class with distinction in BSc as well as in MSc, and after that he qualified 4 times UGC name, and this you can see here he has published he has edited 2 books, and he supervised 8 research scholars, PhD research scholar. 8 scholars are working under his supervision, and he is he is the member of American Chemical Society, Indian Association of Chemistry Teachers, Kerala Academy of Science, Chemical Science Society of India, etc. And he received many awards, and definitely he will in future he will receive number of other awards also, because he will deserve to achieve this. And this means I think 2019 December he makes century in the publication, but now it is 130. So within almost 1 year, he published more than 30 research papers. He has a very active team which he means under his supervision. And this is the research. This is the awards he received, awards and honors. He did a number of postdocs. One I must mention is the JSPS fellow. He did postdoc and from Osaka University, Japan. So with this short introduction, it is our pleasure that sir has agreed to deliver his lecture, and I think our participants will learn many things from his valuable talk. So thank you so much, sir, once again, and welcome you for this webinar. And over to you, sir. Now you please share your slide and please continue. Thank you, sir.
Am I audible?
Yes, sir.
Thank you very much, Dr. Banerjee, for the kind introduction. First of all, I would like to thank the organizers, especially Dr. Banerjee and Dr. Sandeep Kumar, for inviting me to this webinar. I will straight away go to my slides. Can you see the slides?
Yes, sir.
Okay.
Yes, sir.
Okay. The title of my presentation is Carbon-Carbon and Carbon Heteroatom Bond Formations under Green Catalysis. The contents of my presentation has the following. I know that most of the participants are students, so I decided to take some non-named reactions, which I will be dealing with to refresh your memory. And then towards the end, I will also discuss what we are doing at Mahatma Gandhi University, especially these kind of named reactions, how we are doing it, and the application of that in this of heterocycles, those kind of things. But one thing I want to mention in the beginning is that you should not think that all the reactions which I show are green. Like normally we do normal reactions, which will be normal organic reactions with all kinds of solvents, and later we will try to make green reactions. So that is, you will see a journey of our research. So that would be the way I have planned. This slide, of course, by now you must be knowing well the 12 principles of green chemistry. So I don't have to discuss it in detail because already there are a couple of people who might have discussed it earlier. I'll start a little bit with the history of organic chemistry. So actually it started in 1828 when Waller disproved the vital force theory by converting ammonium cyanide to urea. It's a history which all of us know, and that is considered the beginning of organic chemistry, and that was in 1828. And in 1855, the Woods reaction has appeared, which all of us know. That is the alkyl halides, especially iodide and bromide. You can react in presence of sodium to give you hydrocarbons by coupling reaction. And that was in 55. And then in 1862 came the aromatic version of that same reaction, that is aryl halides reacting with sodium, giving you biphenyls, that is the Fittig reaction, and a combination of this we call the Woods-Fittig reaction, which is also known, this chemistry which you have studied well. And in 1869 came the copper promoted Glaser coupling, which also you might have studied. The reaction is actually on terminal alkynes. You can heat in presence of copper 1 in stoichiometric quantity. You will get the copper acetylide, which can be oxidized at a higher temperature, so that a dimerization kind of thing happens, and you get the product. The diacetylene compounds you get, and that was in 1869. And in 2009, a greener version of the reaction has appeared. That is, people have started working on green chemistry, and so an aqueous reaction has appeared. And here, as you can see, water is the solvent which is used. And then in 1901 came the copper promoter Ullmann reaction, which also you study in your BSc and +2. That is, aryl halides react in presence of copper at a higher temperature to give you the biphenyl. And soon after came the Goldberg reaction, which is actually a CN coupling. That is, you react an amide, CONH2 amide, with a halide. So the coupling is between the nitrogen and the carbon here. So you can see here the CN coupling, and of course in low yield the temperature is very high, and a greener reaction of that is also that also came in 2000. That is a ligand-free reaction. Also, the solvent is water. So that is, you can see it here. Water is used as solvent, and this is again a CN coupling. That is modification of that. And then came the Kadiot-Chodkiewicz reaction. Probably you may not be familiar with, which is a terminal acetylene reacting with a haloacetylene in presence of copper on. Here it is catalytic, it's only small quantity you need in a basic condition, which will give you a diacetylene compound. So that reaction is called the Kadiot-Chodkiewicz reaction. And in 1975 came the Sonogashira coupling. That is the reaction between a terminal alkyne and an aryl or alkenyl halide in presence of palladium 0 and copper. So you need both palladium catalyst and copper as a co-catalyst. Both are needed, and that will give you an acetylene compound. So that reaction is called Sonogashira Agihara coupling or Sonagashira coupling. And of course, later in 2009, an aqueous or a green reaction of Sonagashira coupling has appeared, as you can see it here. Okay, and these are chemistry which all of us studied. And if you look the history of palladium catalysis or palladium catalyzed reaction, all these reactions you have studied by now. That is halides, aryl halide or alkenyl halide. You can react with an organomagnesium reagent that we call the Grignard reagent. And there will be coupling between the sp2 carbon here and the carbon in R. That will give you this product. And that is called the Kumar coupling. That was in 1972. And if instead of the organomagnesium reagent, if you use an organozinc reagent, you get the same kind of product. And the reaction is called the Negishi coupling. That was in 1977. So instead of the zinc, if you use a tin reagent, it is called the Stille coupling, which you have studied. If you are using a boronate or boronic acid, then you call it this Suzuki coupling. If it is silicon or silicon reagent, it is called the Hiyama coupling. And if you are coupling the halide with a double bond, the reaction is called Heck reaction. That was in 1972. And instead of a double bond, if you are using a triple bond, the reaction is called Sonagashira coupling, 1975. These are all carbon-carbon coupling. And if you are using an amine with this halide, you get a carbon-nitrogen coupling, so CN coupling. And that reaction is called Buchwald-Hartwig reaction. That was later one, 1994. In all these reactions, we use palladium as the catalyst. And because of the importance of those reactions, Negishi, Suzuki, and Heck shared Nobel Prize in 2010. So that itself shows the importance of this reaction. So this we have all studied. And this is the compiled version of this. That is, you can react halide, alkenyl halide or aryl halide with an organometallic reagent in presence of catalyst, which is normally palladium. You will get a coupled product. And depending upon the metal you use, you have different names. If you are using magnesium, it is called Kumada coupling, zinc, Negishi, boron or boronic acid, Suzuki, tin, Stille, and so on. So this way you can remember it. And there is a general mechanism for all these reactions, which is normally accepted one is palladium 2 is the one which we normally use, which is palladium acetate, and you react that with the ligand, so that will give you palladium 0, and palladium 0 then reacts with the halide. What is happening is palladium inserts into the carbon halogen bond, and you get R on palladium X. So it is actually an oxidation because palladium 0 is converted to palladium 2. So it's an oxidation. At the same time, palladium is inserted into the carbon halogen bond. So it is an addition. So that's why this step is called oxidative addition. And then this organopalladium reagent reacts with the organometallic reagent which we use. This is the Grignard reagent or the zinc reagent, whatever we use. So it reacts with that. And here what happens is this X is replaced by the R2. So you get this R on palladium, R2. So here palladium is 2, here also palladium is 2. And here this is called the transmetallation step because the R2 which is associated with this metal is now transferred to palladium. So there is a change of metal from one metal to the other. That is why it's called transmetallation. So we get this one where palladium is in the 2 oxidation state, +2 oxidation state. And then what happens is palladium from this complex, palladium 0 comes out so that R1 and R2 joins together. So you get the product And you can see that palladium 2 is converted to palladium 0. So it is a reduction. At the same time, palladium is eliminated, or the product is eliminated. So it's an eliminative step. At the same time, it is a reductive step. So it's a reductive elimination. So these are the general steps involved in most of this transition metal catalyzed reaction, oxidative addition, transmetallation, and reductive elimination. So this much chemistry we are all familiar with. I try to to refresh your memory of all these transition metals, and now we will look into what we are doing at MG University, Gandhi University. So we work on transition metals like manganese, iron, cobalt, nickel, and copper, zinc. These are actually less expensive and also less toxic. So that's why we are interested in this transition metals. So initially we started with copper catalyzed coupling reaction. The main reason for starting that is you can see the price of copper compared to palladium. Palladium 1 gram is approximately 5,000 rupees, but copper is only 50 rupees or 42 rupees, so it's approximately 50. So 100 times more expensive is palladium. So we thought of starting our research with copper, and also palladium is flammable. It is also toxicity is also there. That is not there in the case of copper. So this is a good metal to start with, but much cheaper one is zinc, and iron. When it comes, it is much cheaper. It's only 2 point something per gram. The price is. So initially we started with the carbon sulfur bond formation coupling reaction with copper. The reason to use this is evident that there are many drugs which are available in the market having this carbon sulfur bond. You can see that here, in all these drugs, the carbon sulfur bond is formed. So that is showing the importance of formation of carbon sulfur bond. And if you look the literature, how this carbon sulfur bond or sulfide is formed, you will see that it is usually done by reacting a halide with a thiol in presence of palladium 0. So that is the way it is usually made. And for us, we thought of doing it with copper alone, not without palladium, copper, but we have to find the suitable ligand, solvent, and temperature. We have to find out or optimize and get it. And so we started with this reaction with an iodide, with thiol, and with different ligands, different solvents we tried, different bases we tried at different temperatures, and then we found that this is the best condition. That is this ligand. This is L4. That is TAPCO as the ligand, dimethoxyethane as solvent, calcium carbonate as base. At 120 degree, we can get up almost quantitative yield of the sulfide. And so this is the optimized condition. That is copper, we need copper iodide, we need 5 mole%, TAPCO 10 mole%, calcium carbonate 2 equivalents, DME. 120 degrees, 12 hours, we can get this product. And we tried that with different aryl halides and thiols, which are shown here. So here the left part actually comes from the halide and the right part comes from the thiol. So you can see that you can use electron donating group here, electron withdrawing group here, electron withdrawing group here. You can have aryl sulfides, aryl alkyl sulfides. You can have heteroatom here, and any kind of groups you can attach, and the yield also you can see that pretty good. Something around 80 above. And also you can see that there is a gradation in reactivity. If you are using an aryl iodide here, you will get 98. If you are using bromide, 60, which is normal. Here also you can see that if it is chloride is used, the reactivity is much less. So this gradation is quite visible in these reactions. And this is a general reaction, and so we have published it in 2015. And initially we proposed a mechanism, based upon the normal general mechanism of transition metal catalysis. You can make this kind of a species, and then one of these X can be replaced by the thiol, and then the catalyst can, the ligand can come out, and you can get this product. So this was, the initial prediction or proposal of this the mechanism, but later we tried some DFT calculations, and then we found that the mechanism is slightly different. It forms a intermediate first with copper and DAPCO, and then with the thiol it forms a complex or intermediate, and then the iodide reacts and forms this kind of a transition state, where the carbon sulfur bond strengthens, and this bond, carbon iodine bond, weakens, and so you get this kind of a species which will be converted to this transition state. And then the sulfur copper bond weakens, and you get back your catalyst, and this goes back. This goes to the product. So that is the way you can get this the product. So this is after the DFT calculation. So we have developed an efficient copper catalyzed CS bond formation. So that is the conclusion on that research. And we then moved on to Sonogashira reaction, which now we know that it is a reaction between a terminal acetylene and a halide in presence of copper as well as palladium. Both palladium and copper are needed. And we wanted to do this reaction with copper alone without palladium. And for that, we have to find the suitable ligand, base, solvent, all these things we have to do. And we have done the optimization studies by using different ligands, different solvent, different bases, and we found that this is the best condition. 1,4-dioxane, potassium phosphate, you can get almost quantitative yield, and this is the optimized condition. 10 mole % copper iodide, 20 mole % ligand, potassium phosphate base. You can get it in get the acetylenic product or the Sonogashira product. And we did the reaction with different substrates, and the results are shown here. You can use electron withdrawing group here or electron donating group here. That's not giving a good amount of the product. You can have heteroatoms here or here, if possible. The yields are also pretty good. Here also we could see the gradation in reactivity. And then we also proposed a mechanism for this, where copper forms a complex with the ligands. Two ligands are forming, and then one of the ligands is replaced by the acetylide formed from the acetylene. So you can get like this with a solvent molecule, and then the second ligand is replaced by the iodide or the halide to give you this kind of a species. From here, copper 3, copper 1 is regenerated, and you will get the product. So this is only a speculation. We are working on the mechanism of this reaction using DFT calculations. And so here we have developed an efficient palladium-free copper catalytic system for Sonogashira coupling. And yeah, this is the reaction which we have developed, that is copper catalyzed Sonogashira reaction with a terminal alkyne and a halide. You can get this product, the acetylene. in this reaction, if you can introduce an OH group here, then we should get, if this is the reaction, a Sonogashira reaction will happen here, and then the OH group here, that will be here, should cyclize to give you a benzofuran. So this is possible if we have an OH group at the ortho position, and whether we can do such reaction. So we tried that reaction with the different ligands we tried, and we found that the trans-diaminocyclohexane gave 72% yield. All the others are inferior to that. So this we chose as the ligand, and we also optimized the base by using different bases, which potassium, potassium butoxide gave almost quantitative yield. We also we changed or the optimized the solvent. 1,4-dioxane was found to be the best, which 98% yield. So this is the optimized condition for the reaction. 10 mole percent copper iodide, trans 1,2-diaminocyclohexane 20 mole percent, and we took different iodophenols and acetylenes, phenyl acetylenes, and we could get this benzofuran in very good yields. We could also get the alkyl ones, but of course in lower yields. And we also tried the reaction with bromides, which are known that their reactivities are much less, but we tried with the bromides, and the yields are shown here, which is less, as you can see. And we are also able to make this compound, which is cosifuran, which is a natural product with some biological activities. This also we could do it. So that is an application of the Sonogashira reaction. So the mechanism, one can expect the same kind of mechanism up to here, because this is Sonogashira product. So this mechanism is the one which I said earlier, and then there will be a cyclization of this, which is known, and then you can get the benzofuran. And so we could develop an efficient, cost-effective method for one-pot synthesis of benzofuran. We were also able to do the reaction with less reactive bromide, of course, in lesser yield. That is obvious. We then moved to do the Cadiot-Chodkiewicz reaction. The reaction is actually between a terminal alkyne and a halo alkyne in presence of copper to give you diacetylene compound. So this is the sp-sp coupling between this carbon and that carbon. So that is the Cadiot-Chodkiewicz reaction. We wanted to try this reaction to a greener, to make it into a greener reaction. So we tried, and we found that ligand is not needed in this reaction. So at least one reagent we could, remove. And we tried different copper sources, different bases, different solvents, and we found that this is the best condition for that. Copper iodide, potassium carbonate, methanol, 93% you can get the product. So this is the optimum condition. That is, you can use copper iodide, potassium carbonate as base. They're not very toxic, and methanol as solvent, which is also considered a good solvent. Room temperature is the reaction. You don't need inert conditions here. You can use, so that those are green conditions for a reaction. And under these conditions, we could make these products. Here also you can see that there is generality of the reaction is there. You can use many kinds of terminal acetylenes and halo acetylenes, which give the products. Also you can see above 65-70% yield. So and also the reaction is general. So this was published in 2019. We can also propose a mechanism for this copper 1 halide in presence of a base and terminal acetylene, you can get the copper acetylide, and that copper acetylide then reacts with the haloacetylene to give you an oxidative oxidative addition product where copper is in the 3 state. And from here, copper 3, it undergoes reduction to copper 1 and producing the product, the SPSP coupled product. So this is a possible mechanism. Again, we are solely a speculation and we are working on the mechanism of this reaction. So we could develop a very simple and efficient method using no ligand, no amine is used for the Cardiot-Chodkiewicz reaction, and the reaction is done at room temperature, methanol as the solvent, so it is can be considered there is some greenness in this reaction. And yeah, this is the reaction which we have now discussed, that is, if terminal alkyne, you can react with a halide. In presence of palladium and copper, you will get the acetylene, which is called the Sonogashira coupling. And if you use a boronic acid or boronate with a halide in presence of palladium, you can get this product, which is called the Suzuki coupling. If instead of this halide, if you use this halide, that is a haloacetylene, just like here, I put a halogen here, haloacetylene, then you get this product, which is actually, the reaction is Suzuki coupling because you are using a boronic acid. So the reaction is Suzuki coupling, but the product, you can see that product is Sonogashira product. So you can do a Suzuki coupling and you can get a Sonogashira coupling. So can we do this reaction in presence of copper? Normally, Suzuki coupling is done with palladium 0. So can we do it with copper? So that is what we tried. So this reaction, that is haloacetylene with boronic acid with copper, can we get this reaction? So we tried different copper sources, we tried different bases and solvents, and we found that under this condition it is possible to get this product, that is copper iodide. You can take 10 mole %, potassium phosphate, a very mild base, you can use 2 equivalent, and then ethanol, a very green solvent. Under microwave condition, 15 minutes only, you can get this product. So this is, we can consider it as a green reaction. So in all these compounds, we could get the yields, as you can see, are above, mostly above 70. So it's a good reaction, a general reaction, and that is published in 2019. So it's possible to do a Suzuki coupling and get a Sonogashira product. It's also a mechanism, suggested mechanism for that with copper iodide and the bromoacetylene. You can get this copper complex, and then with boronic acid, you can get this copper complex both in copper 3. And then from here, a reductive elimination can happen to give you, to regenerate the catalyst and give you the product. So this is only again a speculation. We are still working on the DFT calculations of this. So for this, we developed a simple ligand-free copper catalyst Suzuki coupling under microwave conditions in methanol. And to summarize the copper reactions, we were able to make the carbon-sulfur bond formation with DAPCO as the ligand, Sonogashira coupling with diaminocyclohexane as the ligand, synthesis of benzofuran with diaminocyclohexane. You could also do the Cardiot-Chodkiewicz reaction without any ligand at room temperature in methanol, and also a Suzuki coupling in ethanol under microwave conditions. We could do that. So these are all about the copper chemistry, and then we moved on to zinc and iron because they are much cheaper than copper, iron and zinc. We'll see how we have done this. Of course, the both are much cheaper than palladium and to some extent cheaper than copper. So initially, we'll see the zinc catalyzed coupling reactions. the carbon sulfur bond formations, we will look, because as I said earlier, carbon sulfur bond is present in many drugs. So it is important to make different ways of having this carbon sulfur bond generated. So this is the reaction we have to perform. A sulfide, a thiol, we have to react with halide in presence of a zinc source, and we have to find out the right base and solvent. We tried different bases, different solvents, different temperatures, and we found that sodium tertiary butoxide in acetonitride 80 degree, you can get almost quantitative yield of the product. And this is the optimum condition we could make, that is titles 8 mole %, proline is an amino acid, very green, 16 mole %. Acetonitrile is also considered a good solvent. At 80 degrees, you can get this product. We tried different thiols, different halides, and the yields are given. The results are given here. Here also we have seen gradation in property. That is, iodide is giving better yield. Here also you can put different groups, electron donating groups. Here most, and of course fluorine. You can also have aryl sulfides or aryl alkyl sulfides. Those are possible. So this is also a general reaction. Yield is also around about or above 70. I think in most cases it is above 70. So this is a general reaction. And that turned out to be the first zinc catalyzed carbon sulfur bond formation. That was in 2015. And then we moved on to synthesis of a CO bond. If CS is possible, then naturally CO bond is also possible, but slightly difficult. That is the only difference. So we tried reaction between phenol and iodide in presence of zinc source with different ligands and bases. We initially tried different ligands. All these ligands we tried, and we found that proline gave 70% yield of this product. Proline is the best one for this, so we took proline as the ligand. And the optimal condition we got was this one: titile zinc 20 mole %, proline 40, cesium carbonate acetonitrile. We could get this product, of course, at a high temperature and a longer period of time. And these are the results we got. So you can see electron withdrawing groups, or iodides are all electron withdrawing groups, which gave not excellent yields, but they are acceptable yields we could get. And also we could change the other side, the thiol part, the phenol part. We could get, we could use electron donating methyl, methoxy, electron withdrawing Cl, heteroatom heterocycle we could get. But when we put electron donating group in the halide, we can see that there is no yield. So this reaction works only in the case of electron withdrawing halides. So that is the disadvantage of this reaction. And this was, the first zinc catalyzed CO coupling reaction. And then we tried to do this Onagashira reaction, which is, reaction between a terminal acetylene and halide with both palladium and copper. And that reaction is called as Onagashira coupling. And we wanted to do this reaction with zinc. So this is the reaction we wanted to do with zinc as the source, as this, as the metal, and suitable ligand and base. We have to get this product. This is what we tried. And of course, I'm not showing any optimization. I'm giving only the final result. That is, with diethyl zinc, you need only 5 mole %. Timida as the ligand, which you need in 10 mole %. Potassium phosphate, 1,4-dioxane, 125 degrees. Longer reaction time, you can get this product. This is what we optimized. So in the optimized conditions, we used different halides and terminal acetylenes, and the results are shown here. You can see that electron withdrawing group, electron donating group, electron withdrawing group, electron withdrawing. So you can use both electron withdrawing and donating groups. And the yields are also pretty good, above 60 or 70 mostly. So the reaction is also general, and that was published some time back. And this was again turned out to be the first zinc catalyzed Sonagashira coupling. And then we moved on to Cadiot-Chodkiewicz reaction, which is usually done with copper as a solvent, terminal acetylene, haloacetylene, copper. We can get this diacetylenic product, 1,3-diacetylene product. So can we do this kind of reaction with zinc? So that is what we tried. And we tried different ligands for that. And we found that proline is the better one with 67% yield. All others are showing lesser yields. And then we tried optimized different solvents, different bases. Different bases also we tried, different solvents, and we found that ethanol, calcium carbonate gave 71% yield or better yield than any other combination. So that is taken as the optimized condition. And for this 20 mole percent diethyl zinc, 40 mole percent proline, calcium carbonate, ethanol, which is also a green solvent, and proline, a green ligand, amino acid, which is used. And these conditions, we tried different substrates, and we could get the Cadiot-Chodkiewicz product. The yields are good, not excellent, I should say. And we could also get some alkyl chain, alkyl attached diacetylenes, but of course in lower yields. We could get attached heteroatoms, heterocyclic group. That's also possible, and that was also published some time back. And this is again the first zinc catalyzed Cadiot-Chodkiewicz reaction. And this paper, this was published in molecular material catalysis, and this is chosen as the editor's choice paper. And then we tried to do the Suzuki reaction. The classical Suzuki is between a boronic acid and halide, which all of us know by now. And what we wanted to do is a previous version of this reaction, that is haloacetylene with boronic acid. So you do a Suzuki and you get a Sonagashira coupling. That is what we wanted to do with suitable zinc source and conditions, because such kind of acetylenes are present in many drugs, as you can see here. So acetylenic derivatives which are used as drugs. So the synthesis of this is important. So that is why we thought of working on that. So this is the reaction we have chosen: the halo-bromoacetylene, boronic acid, suitable zinc source, phase, solvent, etc. So that should give this product. So we tried different zinc sources, we tried different bases, we tried different solvents, and also different ligands, and that gave this product. So the optimized condition was this: 15 mole percent diethyl zinc, 30 dimida, potassium phosphate. You can get this product. So under these optimized conditions, we tried different substrates which gave this product. As you can see, the yields are pretty good. You can use different electron donating groups on the on the bromide, and you can see that in most cases you get about 50-60% yield. And this one, when you use a boronic acid with no aromatic system, then it doesn't work. So aliphatic boronic acid did not give the product. So that is the disadvantage of this reaction. But with aromatic ones, it gave reasonably good yields. And that also turned to be the first zinc catalyzed Suzuki type coupling ever reported. And to summarize the zinc chemistry, we could get the first zinc catalyzed CS coupling, the first CO coupling, Sonagashira coupling we could get, and also zinc catalyzed 1-pot synthesis of heterocycles we could get, zinc catalyzed Cadiot-Chodkiewicz reaction, and also Suzuki coupling. I think I didn't show this reaction, the 1-pot synthesis of heterocycle I didn't show. Probably I removed the slides, but that is also possible, similar to the copper one chemistry which we have seen earlier. And the chemistry is highlighted in one of the issues of advanced synthesis catalysis. And we then moved to iron catalyzed reaction, because iron is considered green, and also it is much cheaper than the other two, zinc and copper. So first we tried the carbon sulfur bond formation with iron. In here we tried iron catalyst with water as a solvent, because then the reaction becomes green. So we took sulfide and thiol and the halide and optimized all the parameters, and we could see that perchlorate 10 mol%, L-proline 20 mol% in water with KOH as the phase, it's possible to do the reaction. So here water is green, proline is also green, iron is also green. So mostly the conditions are, we can consider it as green. And under these conditions, we tried different thiols and halides, and the results are shown here. You can see electron withdrawing group you can attach mostly, and electron donating group you can attach. You can have aryl sulfides or aryl alkyl sulfides are possible. So the reaction is general, and the yield also you can see it's mostly above 70, 65, 70 above. We can see get the product, and that is also luckily the first iron catalyzed CS coupling in water. So we could get this reaction for the first time. And naturally, when if CS is possible, then one should also try CO coupling, and we tried that under water aqueous conditions with iron. We optimized the conditions, and we found that perchlorate 10 mol%, dimida 20 mol% with cesium carbonate 2 equivalent. In water, you can get the ether formation. And the optimized condition was applied using different halides and phenol, and the results are shown here. You can use electron withdrawing group, electron donating group, and you can also see the gradation in reactivity. Different groups you can attach, including the heterocyclic compounds. The yields are above 70-75 degrees, so the reaction is pretty good, and it is general in nature, which is published in Journal of Catalysis. And this is also the first iron catalyzed CO coupling reaction reported. Yeah, this paper is also chosen as a priority communication Journal of Catalysis. And then we tried the Sonagashira type reaction, which the reaction is done with both palladium and copper as the catalyst and co-catalyst on a terminal alkyne with halide. So we wanted to do this reaction with iron, without any palladium, without any copper. So this was the reaction we tried with iron and water. And after optimization, we found that perchlorate 6H2O, phenanthroline, potassium phosphate in water, we can do this reaction. And this condition was applied, and the optimized condition was applied, and that gave this many products. So you can see that the reaction is also general in nature. You can use electron withdrawing groups. You can use electron donating groups like methylamine, methoxy. That's also possible. Heteroatoms possible, heterocyclic compound possible, this side or that side it is possible. And the yield again above 70, so the reaction is pretty good. So that is published in 16. And this is also the first, this was also the first ion catalyzed Sonogashira coupling in water. So to summarize the ion catalysis, we could do the first ion catalyzed CS coupling, we could do the first ion catalyzed CO coupling, and also the Sonogashira coupling, we could do it. Here you can see that many of these functions are green in nature. And then we moved on to manganese, because manganese is also cheap and also it is less toxic. So we tried the CO bond formation or ether bond formation, which is usually done with copper at a higher temperature to give you the the ether. And you can see that the ether link or ether moiety is seen in many important compounds, many drug molecules. So it is very important to make these compounds. And if you look the literature, you can see that several transition metals are used for etherification or ether formation, like iron, cobalt, copper, nickel. All these things are used, but manganese is never used. So we thought of using manganese because it is cheap, it is less toxic. So we tried that reaction with manganese chloride as the salt, as the manganese source, and various ligands we tried like this, and we found that if you use L8, which is this one, dimethyl ethylene diamine, if you use, you can get 88% yield. But it is also seen that if you don't use any ligand, still you can get 72. So that means you can use this, you can do this reaction without any ligand. So we decided to work without ligand. So we again further optimize the different parameters, like solvent we optimized, base we optimized, and we found that acetonitrile cesium carbonate combination can give you quantitative yield of the product. And the optimized condition we tried with different iodides and phenols, and the results are found here. With electron withdrawing group, you can have 99% here. You can also, all this, you can also use cyanide here. So here, all these examples, we can see that electron withdrawing groups on the iodide is needed for this. Then the reaction works. The other side also you can, the phenolic side also you can change phenol, methoxy, methyl at different positions, heteroatoms, biphenyl, naphthalene kind of thing. You can, it's possible. So again, we can say the reaction is generally, except that the iodide should be electron withdrawing, should contain an electron withdrawing group. And this reaction was found to be the first manganese catalyzed CO coupling reaction. And another thing is, here we don't need any ligand. So it's a ligand free protocol. So the reaction is, we can say this is green. And naturally, we can also try manganese first. We can also try with cobalt. So we wanted to try the same ether formation. Normally it is with palladium copper or co-catalyst. We wanted to try the reaction with the cobalt with suitable ligand and solvent. We tried the reaction with different solvents, different ligands, and we found that this one L2. So this one gave 76%, and this one Valine gave 75%. So there is no difference between the yield of these two. And then we tried different solvents like acetonitrile, ethanol, and also we tried different bases, KOH, sodium hydroxide, silicium carbonate, and we could see that acetonitrile silicium carbonate gave 80% yield of the product. And the optimized condition was found to be this, with 15 more percent cobalt, 30 more percent valine, silicium carbonate in acetonitrile of 110. You can get this product, and you can see that the yields are good in most cases. Again, the iodide should be always electron withdrawing on. All are here shown are nitro group. The other side you can change a little bit, and the other side also you can change methoxy without anything, chlorine, methyl, chlorine, the ortho position, all this you can change, but there is some difference in the reactivity or the yield of the product. And inclusion, this was also the first copper free cobalt catalyzed CO coupling reaction reported. And then we wanted to synthesize some heterocycles using transition metal catalysis, if possible, without transition metal also. That is what this we have already seen, that if we take iodophenol and then treat with terminal acetylene, under Sonogashira conditions, if you can apply, this carbon will be connected to this, so you get a Sonogashira coupling, and then this can come here, and you can get the benzofuran. And you can see that different iodophenols gave different benzofurans, which you can see the yields are, in most cases it is good, in some of these cases the yield is not very good. And then we also tried with, instead of iodide, we also tried with bromo, because bromo compounds are less reactive. So we tried that, and that also worked, but of course naturally with less yield, so we could get the corresponding products in lower yields. And also an extension of the Sonogashira coupling, that is, if you have an OH group here, you should be able to make a Sonogashira coupling here, followed by the cyclization to give you benzofuran. So in that way we were able to make this many benzofuran derivatives, including aliphatic compounds. And then instead of an OH group, if you can put an NH2 group there, then naturally you should get an Indian Indian skeleton. And when we did the reaction, what we got was a mixture of this one and the uncyclized one. The NH2 was free in the ratio 3, 1:3, 1:2. So this is 30, this is 60, so almost 1:2 ratio could get, and this is the required product, and this is the uncyclized one we got in large quantities. So to circumvent that, what we did was, after this reaction, to the reaction mixture we added. So after this reaction, we added some stronger base, so that this will cyclize to give you this product, and it happened. So we could get, after doing this reaction, we could get the product in and 1 or 2 compounds we could make in good yield. As you can see, 90%, almost 75% almost, we could make this product. So it's it's again possible to make a nitrogen heterocycle or a oxygen heterocycle. And then we moved on to the synthesis of imidazopyridine. The structure I will show you. This blue one is the imidazopyridine. There's an imidazole, that is 5-membered ring with 1,3 nitrogen, this imidazole. and then a pyridine 6-membered with one nitrogen that is fused together. So this is the imidaz of pyridine, and this skeleton is present in many important drugs like solpidem, alpidem, solimidine, and others. So the formation of this structure is important. So we try to make this kind of skeleton. And if you look the literature, how this has been made, you will see a reaction probably you are not familiar with, which is the Ortoliva-King reaction. And the reaction is this. You take a ketone with a alpha enolizable proton. So you take that ketone and react with iodine. When you react with iodine, you can get the alpha iodo-ketone. Alpha iodo-ketone you can get. And that, if you react with pyridine, what happens is the pyridine lone pair can attack here, and then the I can be eliminated. So pyridine will have some positive charge when it attacks here, and then this is gone. So you get this kind of a pyridinium salt. Okay, and this one, if your starting material, this pyridine has an NH2 group here, then it is called aminopyridine, and the product will have an NH2 here, right? And that NH2, if you are using an NH2 here, that NH2 formed here can condense with this CO, and you get a cycle. So this is what's shown here. So you have the ketone, you react with iodine, so you get this, and you treat with aminopyridine. This lone pair will attack here, and you get this kind of a species, and here you have an NH2, and that NH2 will condense with this CO, and you get this imidazopyridine. That is called the Ortoliva-King reaction. But here the problem is, here iodine is used stoichiometric or excess, because you need, for each one you need one iodide. So so here also the reaction is stoichiometric, so you need a stoichiometric amount or excess of iodine. What we have tried was the same reaction with an enolizable ketone with aminopyridine, but we wanted to use the iodine as a catalytic amount, and also iron we wanted to use catalytic amount. So we wanted to do a catalytic reaction. Originally the reaction was a stoichiometric one. We wanted to make it a catalytic one, which is the principle of green chemistry. How we can do that? That is what we tried, and we tried different conditions, and we found that it is possible to do the reaction in a catalytic fashion with ferric chloride 6H2 20 mole percent and iodine 20 mole percent. With chlorobenzene, you can do this reaction. This is what we found, and the optimum condition was given, was applied to different ketones and amines, aminopyridines, and these are the products which we could get. You can see differently substituted aminopyridines and differently substituted ketones. We could get these many products. Here the yields are not excellent, as you can see. It is something around 50-60% we could get it, and we were also able to make in one pot this solimidine, which is a drug available in the market. So we were able to make the imidazopyridine. And we also propose a mechanism for this, where the ketone reacts with iodine, or ketone comes in close contact with the iodide, and then you get the alpha iodinated product that will liberate an I minus, and then this will react with the aminopyridine to give you this pyridinium salt. That will pyridinium salt, and then that liberates an I minus, because when this is formed, an I minus is liberated. So there are two I minus, one coming from here, one coming from here. And this then can condense and then give you this product which eliminates molecule of water, and you get the product. Yeah, here the product. And the I minus formed is actually converted to iodine by iron 3. Iron 3 is converted to iron 2 so that this I minus will go to I2. So that way you can get back your iodine. So this is only a proposed mechanism. We have to do calculations and see how this is working. And this was also the first iron catalyzed Otto King reaction. And then we tried to make the 2-amino-thiazole, which is also present in many drugs. As you can see, these are some of the drugs having this skeleton, and synthesis of that is important. So if you look the literature, how thiazoles are made, it is by heating, by reacting a alpha halo ketone with thioamide, you can get this. And there's a modified version of this where you can use, instead of this halo ketone, you can use a ketone and you can add iodine, so that stoichiometric, so you get this compound formed, and then reacting with this one in situ generated, and then it reacts with the thioamide and gives you this one. That is also possible. And what we wanted to do was the same reaction, but with catalytic amount of iron and catalytic amount of iodine. So this is not a catalytic reaction. So that is what we wanted to try. So this is what we tried. The ketone we took, and instead of thioamide, we took thiourea, because that is easily available. And then we tried iron and iodine. And after a lot of optimization, we could see that this was the optimum condition, and which could give this amino-thiazole. So we made different amino-thiazoles. Of course, the yields are acceptable but not excellent. In that way, we could make the amino-thiazoles easily and under green conditions. And this was also the first iron catalyzed amino-thiazole synthesis with iron as the catalyst and PEG. This is considered a green solvent. So we could do some green chemistry, and also then synthesis of pherols. Pherol is very important because it has a large number of properties, medicinal properties, with these kind of anti-viral, anti-inflammatory cancer properties. So we wanted to make this reaction, and there are many drugs having this core skeleton of pherol, including the atorvastatin, which is for the cholesterol lowering drug. If you look the literature, how these pherols are made, there are many name reactions like Hansch pherol synthesis, Nor pherol synthesis, Polno. These are all probably you might have studied. At least the first three you might have studied. So this is a commonly used one, Polno pherol synthesis. This was reported in 1884. The reaction is, probably you remember, it is 1,4-diketone. You can react with amine to give you this one, the pherol. So that is the reaction. And there are modifications of that. That is called the Clausen-Cass reaction, which was reported in 1952. The reaction is you use the same reagents, that is the amine, and instead of the 1,4-diketone, you use a masked 1,4-diketone, that is 2,5-dimethoxy tetrahydrofuran you can use in presence of acid. So in presence of acid, this will be cleaved and this will go back to the 1,4-diketone, and then that will react and will give you the pherol. So that is the Clausen-Cass reaction, which was discovered by Clausen-Cass. His name is pretty bit big. It's a simple reaction. So we tried this reaction. We looked in the literature and we found that the reaction, Clausen-Cass reaction, is done with cerium, with copper, with iron, with zirconium, with manganese. This is all known, but it is not known with manganese. So we tried this reaction. And we found that it is possible to do this reaction with manganese nitrate, tetrahydrate. You don't need anything, just microwave, 20 minutes you can get. No solvent, nothing is needed. So that is a green reaction. So we could make these pyrrole derivatives in reasonably good yields, and that is now submitted. And so this is a environmentally benign reaction because manganese is considered green and good yield, short reaction temperature, reaction time. We are using microwave. So this is considered a green reaction. And then we moved on to the synthesis of pyrimidines. Pyrimidines are having this structure with an naphthalene with 2 amino groups connected by a one carbon system. That is called pyrimidines. They have very good, large number of properties, biological properties are there. You can see that anti-cancer properties, antibacterial, those kind of properties are there. Also, material properties are also there. As dyes, protoxines, and all these properties are there. So this the skeleton is quite important. So we tried to make this reaction bit greener. So for that we wanted to do this reaction in an on-water reaction. That is what we tried. So we took the diamino naphthalene with aldehyde in water, just 30 minutes at room temperature. We could get the product in 99% yield. There is only water as a solvent, so this is a truly green synthesis. In this way, we could make about 28 examples with aldehydes. But one thing, the yields are, you can see that it is pretty good, except when you come to the last portion where we used ketones. You have to hear it is aldehyde. So when we use ketones, it didn't work. There is nothing detected. So ketones did not give this reaction, but aldehydes gave. So that is a disadvantage of this reaction. And we could also scale up this reaction in gram scale. 5 grams of this, 4 grams of this we could make, and that also gave almost 90% yield. So the reaction is pretty good. And then, so this is a mechanism we have suggested for this. And then we wanted to do the reaction without even solvent, that is by mechanochemical way, that is take the 2 substrates and just grind it, and then we can get it in 5 minutes. We can get the product in good yield. And this way we, this is the way. You just take the 2 components, substrates, and grind it. So initially you will get it like this, and then get this kind of product which can be recrystallized to give you, pure compound. So you don't have to do column in most of the cases. If the yield is high, you don't have to do column. You can do the crystallization and get. So in this way, we could make 24 examples. Here also, the ketones did not work because that ketone is less reactive. That is why it didn't give the products, but the aldehydes did. And then with the ketones, what we can do? So we tried to do the reaction with ketones. And so we have to activate it. We looked in the literature how that is possible. So in literature, people have used ruthenium, bismuth, ytterbium. So those reagents were used to activate it and get the product that is known in the literature. And so we also wanted to do this reaction, but in a greener way. So what we did was we did the same reaction in water, but as a to activate that we used PTSA, para-toluene sulfonic acid, which is a mild acid and it's not very toxic. And that gives this product. So we could get 22 ketones converted into pyrimidines with very good yield, and that is shown here. So this is now accepted in heterocycle. So in the case of pyrimidines, we could get the first catalyst-free reaction, first mechanochemical reaction, and also a salt acid catalyzed reaction on ketones that was also we could make. And to summarize this, we could, we tried to show you some copper catalyzed reaction, zinc catalyzed reaction, some green chemistry on iron, manganese, cobalt, and also some synthesis of heterocycles, including pyrimidines. We could show you. And this is all the group. All the students, except this person, all have left the group. And of course, they were the people who did the copper chemistry with these two people, Singh, these two people, and the pyrimidine chemistry, Nisi has done, iron chemistry, Sindhu has done. This is also old, only this person is still there, and she's also still in the group. And I should thank thank my university for giving me the facilities, and funding came from KCST state funding, and also from Electronic Industries Germany. I also thank the organizers for inviting me to this webinar. And also I would like to show you the latest book which will come in 28th of the hard copy will come out in 28th of this month, but the e-copy is presently available. And thank you for your kind attention. I think I took 5 minutes more.
Thank you so much, sir. Thank you for your valuable lecture. You have explained various aspects on coupling reactions, like by avoiding palladium as a catalyst. Also, you can perform this coupling reaction like copper catalyzed, zinc catalyzed, iron and manganese. You have applied. I think I'm sure our participants have learned many things from your lecture. So our next speaker, Professor Basu sir, is waiting. So thank you so much, sir, once again. So now I'm requesting Professor Basudeb Basu sir. Sir, can you hear me? Basudeb Basu sir, can you hear me? Basudeb Basu sir. So, dear participants, if you have any question or if you want to share your views with Professor Anil Kumar Gopinathan sir, you please unmute and share your views. And I think somehow Basudeb Basu sir just disconnected. So, dear participants, if you have any question or you can share your views.
Good afternoon, sir.
Yeah.
Thank you, sir. Thank you so much for your valuable time. And lecture was very interesting, and we learned so many things from your lecture. It was very informative. Thank you. Thank you so much, sir.
Thank you.
देख लीजिए पोस्ट करना भी Hello, sir. Can you hear me?
Hello.
Yes, yes, sir.
Yeah. I can.
Okay.
Yeah.
Thank you, sir. So, dear participant, our next speaker is Professor Basudeb Basu, sir. He is just a minute. Let me share. His CV. Just a minute. Just a minute. So, our Professor Basu, retired professor of chemistry from Department of Chemistry, North Bengal, University of North Bengal, Darjeeling. He did presently he is a visiting professor at Raiganj University, and he did his PhD from cultivation of science in 1985, and he did masters from North Bengal University in 1977, and after that he was right now he is the visiting professor at Raiganj University. Before that, adjunct professor from Kottayam University and professor of Sabo, Department of Chemistry, North Bengal University since almost.
I think you short the introduction and allow me.
Yes, sir. Yes,
already.
sir. As there is a lack of time, Professor Basu supervised more than 17 research scholars and published more than 160 research papers. So, as the time is because of lack of time, I am over to you, sir. You please go through your presentation and share your scheme, and we'll start the presentation. Thank you so much, sir.
Okay. Thank you, Dr. Bubun Banerjee and Dr. Sandeep Kumar, who also sent an email today giving the link address and requesting me to join you. And I like to express my thanks and regard to the head of the Department of Chemistry and Akal University Authority for inviting me and giving this opportunity to discuss with you. Now, first of all, I like to share the screen and then please hold on, because this process is going on with Zoom and I am used to Google Meet. Let me see. Share. Okay. Yeah. Is that slide is visible to everybody?
Yes, sir. Yes, sir. Sir, can you please start your video as well?
Video.
Yes.
Okay. Where is video? Start video. Yeah. Okay. So I think one can see me and also
yes, sir.
The slide.
Yes, sir.
Okay. So it is better to put it on the slide apart from the slide. So thanks to all of you first of all, dear audience, it is already 25 minutes late, and you have been listening lectures since morning. So I think you are a little bit tired, but still I like to thank Dr. Banerjee for his introduction. Although there will be little change in my present position. As you can see, I am presently an adjunct professor at Cotton University in Assam, and I have already completed my tenure as primarily as visiting professor of chemistry in North Bengal University and visiting professor at Raiganj University. So today, coming back to the actual topic, I will try to finish within 45 minutes. But let me give you some introduction, a fascinating world of graphene chemistry, which are generally called carbonaceous nanomaterials. And this is a good opportunity that recent trends in green chemistry organized by this chemistry department, Akal University. Am I audible to everybody?
Yes, sir.
Okay. So the title I have chosen, as you can see, this functionalized carbonaceous nanomaterial in catalysis. Now, just to catalysis, if you just read through the very first book of Paul Anastas, who is sometimes referred to as the father of green chemistry. In one of his books, he wrote that catalysis is one of the foundational stone of green chemistry. So it is indeed a fact that catalysis is a very much part and parcel of green chemistry. And now, if you come to the carbonaceous nanomaterials, mainly the nanomaterials, as you all know, that nanomaterials are widely used in various purposes. But here we will talk on only carbon. So we will be introduced shortly. Now, before describing this carbonaceous nanomaterial in the introductory part, let me just tell you about the catalysis or catalyst. The term was coined by, all of you know the catalysis is that generally makes a process faster without having its change at the end. This is the general definition we learned from class 12 standard. And the term was coined by this scientist Jan Berzelius, a Swedish chemist, who is actually known for inventing some elements. But he actually coined this term catalyst or catalysis. And all of you know that most biochemical processes involve enzymes as catalysts. And if you just look through in industrial processes, there are many metals, and just you have heard the lecture of Professor Anil Kumar, who has shown many examples of metal catalyzed processes, chemical transformations. And nearly 90% chemical industries has catalysis related process. And annual turnover is quite a good amount, is $25 billion in this 2020 sometime. But today, I'll be talking on, or rather, we'll be familiarized with this carbon nanomaterial. So if we just concentrate on carbon, now this carbon, all of you know, is a coal is a carbon, and carbon touches many aspects of our daily life. And how do we get the charcoal? If we burn this wood, if we burn this wood under a slow stream of oxygen, then the charcoal is produced. And also coal is a fossil fuel that we get, in the on the earth crust. And this carbon actually touches many aspects of our daily life in general. Say, for example, water purifier, air purifier, to reinforce tires. Then fiber composites are used. Carbon foams are used as fire retardant. Petroleum coke is used to manufacture graphite electrode and recycling iron and steel, etc. And all of we know that carbon constitute a major part of organic and biomolecules, as well as the carbon cycle. So carbon is, encompasses our daily life and also various parts of chemistry. But as I told, today I'll be talking on carbon nanomaterials. So what is carbon nanomaterial? So there are some aspects, particularly the allotropes of carbon. Allotropes of carbons, like diamond, graphite, lonsdaleite, fullerenes, buckyball, commonly known as amorphous carbon, carbon nanotube, and these are having different structures. So all are carbons, they are called allotropes, so carbons. And just graphite is well known, and graphite is mainly uses in refractories, batteries, steel making, etc. And India uses only 3% of graphite material. So graphite is very unique in structure, as you can see, is benzene ring. All carbons are sp2 hybridized carbons, and they are arranged like honeycomb structures, 6-membered rings attached one after another, and it's like a sheet. So if you have this, this sheet, and they are stacked one after another in bulk material. If we just try to peel it up by removing layers after layer, for example, if I remove this layer, and then you try to remove another layer, or we try to another layer, then ultimately you get this only single layer that is called graphene. So multiple layers of graphene, actually the bulk material graphite, and if we get the mono layers, then it is called graphene. So this is the basic difference between graphene and graphite. So these are different layers of this. So basically, graphites, they are stacked one after another, and only single layer, mono layer, is called graphene. Sometimes we can have bi or tri or few layers of graphite, which are also graphene because they do behave like a graphene material. And this is a nanosheet because only 2-dimensional and 1 carbon atom thick. The thickness is 1 carbon atom and 2-dimensional. So it is 2-dimensional material, and thickness is only with 1 atom. So it comes under nano species. Okay. Oh, what happened? No, sorry. It comes. Yeah. So these are 2 or 3-dimensional graphene materials. And here is a funny, comparison. I hope everybody can see that this is a potato. So if you just peel it, potato, and then, or rather slice it, then it looks like, each layer of potato. And then what do you do with this? We fry it, and it gives a delicious potato chips. So basically, if we just compare between graphite and graphene, it's like your the graphite. This is your graphite, that is potato, and this potato chips or the slices, single layer, then it is called graphene. So this is the primary difference. So graphene is, as I told, that each carbon is sp2 hybridized, and single layer sp2 hybridized carbons is a two-dimensional carbonaceous nanomaterial. And this is the thinnest material and robust and excellent conductor because pi electrons are present on the surface. And it was first invented in 2004 by Scotch tape method. And they produced high quality material. And for that, this Jaim and Konstantin Novoselov, they were awarded Nobel Prize in 2010. But these two scientists who developed this graphene material, they are actually physicists, and they were awarded Nobel Prize in physics. But as people see or find that graphene materials can be, used for diverse purposes, as well as it can be functionalized and use it in different purposes as well. So one needs in bulk quantity, and physicists cannot make by Scotch tape method in bulk quantity. So here the chemist jumped into it and played the key role to demonstrate or develop the processes or procedures of making graphene material in bulk quantities. So here again, pictorially, I'm trying to show you, just to impress upon the young budding students or audience, that this is a single layer, and these are stacked layers. So this is graphene monolayer. This is graphene three layers, or if there are thousands or crores of layers are stacked, then it is graphite. And if you just roll it like a cylindrical, then it is called carbon nanotube or CNT. So we will be talking on this graphene monolayers item. And let's see some of the little more properties. As you can see, if it is sp2 hybridized, so it is the non-hybridized p lobe, and these three are hybridized. So each carbon, okay? So each carbon is sp2 hybridized. And the mechanical properties is exceedingly high. For example, it can be, the strength can be detected or use a technique called atomic force microscopy. It is 300 times harder than steel. Tensile strength is 1 terapascal, means 1 trillion Pascal, what is called terapascal. And it is slightly stretchable like elastic in nature, 20% of its initial length. It is stretchable. And it contains all pi electrons, so it is a high conductor of electrons, can conduct thermal conductivity as well as electrical conductivity. Coming back to this catalysis part, the catalysis, always you know, it is a surface phenomenon. And I just show this scientist photograph, Gerhard Ertel, who actually demonstrated or discovered some of the major properties by which the catalytic functions are played on, and for which he was awarded Nobel Prize in 2007, which are surface phenomena and intrinsically a nanoscale phenomenon. So when you have a nano surface, which obviously is having a large surface area, it can exhibit a better catalytic performance than its bulk material. So I'm going to show you the methods by which these graphene materials can be prepared. The graphene materials can be functionalized and can be further used, or the graphene materials can be utilized as a surface to hook up or immobilized with metal nanoparticles for further application in catalysis or organic reaction. So some of our work I am going to discuss with this carbonaceous graphene material. So how it was prepared in a bulk quantity that chemists actually developed. So you take the graphite powder, very simple. One can use it in very simple laboratory, not in well equipped one, but still you can make. You just simple oxidize it, and oxidation can be done by various means. I will show you some of the methods, but one or two methods are people often use. So if you oxidize it, you can easily imagine that this is a surface, so the bonds can also be oxidized. So what will happen? Terminal carbons will be oxidized to carboxylic acid. Internet connection is okay? Can you hear me?
Yes, sir. Yes,
okay.
Sir.
Okay. So the terminal carbons can give you the carboxylic acid group, and most double bonds can be oxidized, so epoxides or hydroxylated, something like this. So this is the general, structure of this graphite oxide. So once you produce after oxidation the graphite oxide, you can exfoliate it. So this is the general chart. You take the graphite powder, you oxidize it so that you oxygen functionalized graphite oxide. And then exfoliation can be done by using sonication or ball milling so that the layers are being separated under dispersion in water. So you get monobi or few layers of graphene oxide. And this graphene oxide, when you reduce it, it can be reduced very easily and by various means. I will show you a few of the examples later on. And then you get the reduced graphene oxide, where the carboxyl groups are decarboxylated, the double bonds are being introduced. The pi network again will be introduced so that it is almost nearly equivalent or behave like your graphene nanosheets. One is Humer method, long known, more than 60, 70 years known. And there is another method is Toots method that was discovered or published in 2010, 10 years back. So initially in our lab, we used to apply this method, but later on we found that this is better method, the Toots method, and we started working after 2010. So mostly we have used this method of Toots. As you can see, there is a table where Brody's method. There are many methods, but Humer's method and from 1958 and Toots method 2010. So this is simply oxidation, not that the exfoliation or the nanomaterial preparation. So this was done after 2010 or yeah. So graphite oxide can be converted to reduced graphene oxide that can be done by simple solvothermal process, by using various chemicals, reducing sources like hydrazine, borohydride, aluminum hydride, metal HCl, so many chemicals. And sometimes the natural sources like ascorbic acid, amino acids, or even green tea extracts. I'll show you a few examples. So anyway, let's concentrate on this graphene oxide first. And the most common structure, there are various structures have been proposed by different scientists because it is not exactly known. But this is the most common, and people accepted the structures where it contains the peripheral sites, mostly containing carboxylic acid. So it behaves like an acid, and you will find in pH in aqueous suspension around 3.4. and the internal double bonds are affected, therefore you get these epoxide or hydroxyl groups. So there are oxygenated functions like carbonyl group, oxygen group, hydroxyl group, epoxide group, and carboxylic acid group. So in one way, it can behave like an acidic function, and the other way, it can behave like an oxidizing material because it can be easily reduced to graphene or reduced graphene oxide. So it has got some oxidizing ability. At the same time, the terminal acidic functions can exhibit some acidic function. It is very interesting. So various functionalizations that people tried. I will show you some of them. So the first example that I like to show that was first published in 2010 by Christopher Bilawski. What he did, he showed that graphene oxide can be used as a catalyst for oxidation. Since graphene oxide can be reduced very easily, so it can oxidize this secondary hydroxyl group to ketone. And also that started working on it. And we found that the Bilawski's first seminal paper in 2010 in Angola, you will find they obtained in 13 to 98%. So that actually struck to our mind that why this wide range for this secondary alcohol to ketone? Is there any other competing reaction there? Because graphene oxide, as I showed you, it contains the acidic carbon. So if this hydroxyl group is being protonated and you have this alpha hydrogen, so why not? And at the same time, this carbon is a benzylic carbon. So as an organic chemist, if you look at this molecule, there is a possibility of dehydration so that you get this styrene bond. So we thought that whether there is a competition, and that's why possibly Bilawski got this wide range of yields in different purposes. Sometimes it is oxidizing quite nicely and sometimes some other products, so they ignored it. So we tried under different conditions, under different concentration or loading of this graphene. We were able to isolate the styrene material, but the yield was not that good. Again, 40 to 45% the styrene instead of oxidation. So instead of oxidation, one can get the dehydrated material using the graphene oxide under different loading and under different temperature. And particularly if you just avoid oxygen atmosphere, so you perform the reaction under a blanket of nitrogen. So what we thought that if we just have some reacting material within the system, that the styrene double bond can further react so that the reaction equilibrium can be shifted on the right hand side. So what we tried, we took this material and graphene oxide and a thiol, because thiol is known to be added to the double bond very quickly, what is commonly known as click reaction. So we added thiol, and we indeed got this product. So it is a click reaction. And then the yield was quite excellent, about more than 90% yield under blanket of nitrogen and controlled temperature, and only 10 milligram by weight. So 200 weight % was used by Bilawski, and we used only 10 milligram per millimole. So that was the procedure that we first developed, and neither alcohol nor the thiol oxidized, rather reacted differently. And that was possible under controlled use. So we first published in 2013 our observation. observation of graphene oxide materials. Initially, it was about to be published in ChemCom, but finally, it was suggested that I should transfer it to RSC, Advanced Essays, because one referee had some reservation for it. But anyway, so we performed it, and we showed that control use of graphene oxide can perform the reaction in different route or different way. So then we did various applications, a couple of applications I'm going to show just very quickly, that you can see that thioacetylation can be done. There are many examples. You can see that only same type of thiols, internal cyclic thioacetal, or two types of thiols, so that you can get so various type of methods. And the graphene oxide remains more or less fairly similar, and you can recycle it. So no metal, nothing is there. So no toxicity, only graphene oxide. You prepare it and apply it in different reactions. So then another example, we proposed a mechanism also. Then again, nitro-2 aniline is well known, and that we tried in presence of hydrazine. So aniline, in one part, we ultimately ended up with quinoxaline, one of the important heterocyclic scaffold. So that can be done because dianilines or orthophenylene diamine is not quite stable. It can be oxidized under aerial condition even. All of you know that this material is used as a hair dyer. But nitro halo compounds or nitro anilines are pretty stable, so that can be used. So this material in one pot can be reduced and followed by quinoxaline can be prepared. And then another example is that this aminothiol, if you take and 1,3-diketone, then graphene oxide is very selective. You get different products. It is a benzothiazine and this azothiol. So this type of different mechanisms played with graphene oxide, and you see this is tosoic acid, paratoluene sulfuric acid. So there are various ways. The last one, and this example I'll show you, and Professor Anil Kumar was showing this imidazo alpha pyridine, 1,2-pyridine, which are very common drug materials. So this is imidazopyridine, and you will find some other, with this 1, 2, 3 position with a sulfur. So that 3-sulfinyl imidazopyridine. This is very important. So graphene oxide was used. Again, this is possibly, if you try this one, there are various intermediates are formed, and people believe that ortoleva king intermediate, what was discussed just by Professor Anil Kumar. So simple reaction, but if you try with graphene oxide with sodium iodide, not with iodine only, because incipient production of iodine from this graphene oxide, that is very reactive, and so that you get all these 3-sulfinylated products. So sodium iodide is oxidized. This is your ortoleva king type of intermediate, by which the reaction proceeds, or through which the reaction proceeds. It catalyzes in forming ortoleva king type of intermediate, selective addition of thiol, and further oxidation. So again, we published. Then a CH activation. All the hydrogens are not that active, only aromatic, So here you can make this carbon-sulfur bond in all these cases by using your graphene oxide in presence of sodium iodide. So that we demonstrated and proposed a mechanism and recyclability also. So these are some examples. Again, transamidation process, again with graphene oxide. So I'm going a little quickly just to establish in your mind that graphene oxide can display various examples or various organic transformations. And this is a new one. this one is graphene oxide as a catalyst that was published in 2014 by other group, and they obtained this pyridine ring, substituted pyridine. But we wanted dihydropyridine, but dihydropyridine, you cannot stop the reaction at this level because graphene oxide is highly oxidizing property, is having high oxidizing property. So dihydropyridine can be easily oxidized to pyridine. So what we did, we rationalized by minimizing some of the functional group with the silyl group and terminal aniline group, so that you have this acidic group as well as amine group. It is a bifunctional catalyst with amine functionalized graphene oxide nanosheets, commonly known as abgons, that we denoted with these abgons. And this is having less oxidizing property, but with acidic property. And acidic property is again controlled with the presence of aniline. And because of this functionalization through silicon, it cannot be easily reduced. So its oxidizing ability has been reduced or controlled. At the same time, its acidic property is controlled. So that can be used very nicely in a 3-component or 4-component reaction to produce 1,4-dihydropyridine and also polyhydroquinoline derivative. So all these heterocycles were synthesized using this graphene oxide. So we proposed a mechanism by doing several control experiments and possible mechanisms. And last but not the least, this is example is the continuous flow. This is a very modern technique. Now most of the pharmaceutical chemistry laboratories are using. It's like controlling or mixing your ingredients or the reacting partners or the substrate molecules at different flow rate or different temperatures, adding one after another, and you get the product. You can drain out the product from here, or final product you get and you drain out. So it is a continuous flow reactor. What it means, you don't need to separate anything. So you mix them up, do the reaction under this temperature, controlling temperature or pressure, etc., or stirring, etc. But these equipments are you have to purchase and quite costly nowadays and commonly used by pharmaceutical companies. So we made, or rather we demonstrated in our lab in an indigenous process, by using graphene oxide bed here, and there is the ice jacket to control it. So that what we did, we first used aryl amine and a diazotizing agent so that it will be diazotized. So you will get ArNH2, followed by treatment with thiol in acetonitrile at a controlled rate. You can see this milliliter per minute. So there are 2-step reaction through the graphene oxide bed, but in a continuous flow type, and you end up with this, thiol product. So carbon nitrogen bond is being replaced with carbon sulfur. So this is the process that we published, in last year. So this is a continuous flow type. So coming back to your reduced graphene oxide, that as I told, that the pi electron source or pi electron network has been reintroduced from this graphene oxide with few of these terminal carboxyl or hydroxyl group, and the pi electrons are on the basal plate. So this is your graphite and graphene oxide and reduced graphene oxide pictorially presented. Oh, sorry. Again, sorry. Yeah. So as I told that there are various means. So in our MSc project, students did some projects with a different plant extract, and I show you here some of the tea plant or some other mushroom extracts, etc., natural products. So there are extracts, and I just show by image. You will see that if you just graphene oxide dispersion in water, and if you mix with tea leaf extract in water, very simple. You mix them together, you get dark colored suspension. So the graphene oxide is brownish in color, and reduced graphene oxide is black in color. So by color, you can easily identify, but it is only visibly you can see, but you have to, centrifuge and isolate and characterize it, the reduced graphene oxide. That is. So this was also done by other groups from National Chemical Laboratory in 2011. And we wrote a very big article in Current Graphene Science in 2017 by using, various means. And what we found, you can see the pH. Graphene oxide pH is 3.10, whereas if you use the reduced graphene oxide, you see the acidic property is reduced or the pH is decreased. So, and by using different sources, you can have slightly different properties that was measured by different, measurements, pH measurement, cation exchangeability, or potentiometric titration, etc. So all these things. So this reduced graphene oxide can be used as a good support for embedding metal nanoparticles. So first example about is nickel 0. Nickel 0 is very difficult to keep on because it will be readily oxidized to nickel 2. So again, here is a process where we are able to immobilize nickel nanoparticle embedded with reduced graphene oxide because it is already a pi electron rich source. So it cannot be easily oxidized because to oxidize the nickel 0 to nickel 2, nickel has to release the electron. And since you have the pi electron rich source, the release of electron becomes difficult. So that way we are able to stabilize nickel 0 nanoparticles. Okay. So this is nickel embedded reduced graphene oxide that was used as a characterized by different spectroscopic methods and transmission electron microscope, etc., and used in a carbon-carbon coupling reaction. You can see this is your Koryo-Kumada coupling reaction with nickel RGO. So, and that was published in 2014 anyway. So anyway, and it is recyclable. So for various runs. And after the reaction, we also characterized by Raman spectroscopy and XRD analysis, etc., and everything showed quite nicely. And this is another example where this nickel species, the stabilized nickel 0 can be used for making this carbon sulfur bond by simple coupling reaction, cross coupling reaction. But one thing that we had observed here, that nickel 0 gradually is oxidized. So during the course of the reaction or even at the time of workup, the nickel 0 is not, we are not able to keep nickel 0 or hold up nickel 0, rather it is oxidized to nickel hydroxide. Still it is active, and in this work we demonstrated that nickel hydroxide nanoparticles of specific sizes or nickel 0 particles of specific sizes that were effective for this carbon sulfur coupling reaction. But still we are searching on, and I will show in the last slide another success that we have been able to recently, and that was published in 2021 this year. But before that, I want to show you another example of manganese dioxide as a catalyst oxidizing agent. But this manganese dioxide on, again, amine functionalized graphene nanosheets on which the manganese dioxide was deposited, but manganese dioxide nanoparticles that were produced from potassium permanganate under slightly alkaline medium, because amine groups display some basic medium, so slightly basic medium. So manganate can be reduced to ultimately manganese dioxide, and the growth of this manganese dioxide to nanowires. So it is one after another, it deposits. So that way we characterized it by various means, and finally you can see here in a higher magnification of with field emission scanning electron micrograph that manganese dioxide nanoparticles are deposited one after another. And further, a bright field transmission electron microscope also demonstrated or clearly showed that manganese dioxide nanoparticles are arranged or growth was like that, the nanowire. So this nanowire was applied then in, application for oxidation. So manganese dioxide is known to oxidize, benzylic alcohols or allyl alcohols very nicely. But only thing, the importance of this method is that there is a synergistic effect of nanowire electron-rich surface as well as the amine, enhancing the process of electron transfer. But one important point is that manganese dioxide is well known for oxidation of this alcohol. But once you perform this reaction, you will need high excess quantity of manganese dioxide for oxidation. But here, we used only 7 mole %. So apart from 200 mole % of normally required in industrial processes, we have shown that if we can prepare these amine functionalized graphene nanosheets embedded manganese dioxide, only 7 mole % use of this manganese dioxide is enough to oxidize this alcohol. And the last work that we have been able to recently shown as a ternary composite of zeolite and reduced graphene oxide, because all of you know zeolite are hexagonal, macroporous material, and here zeolites consist of tetrahedral structure with this aluminate and silicate, but you can see that aluminate with 5 negative charges and silicate with 4 negative charges. So there is a formal protonation is required, and that can balance the negative charge resulting hydroxyl group with aluminum oxygen silicon bond, which could serve as the Bronsted acid site. And the silicon site is the Lewis acid site. So what happened, what we did, or what we thought, that whether graphene oxide can supply these carboxylic acid protons to supply this H plus or formal protonation, then we can have this Bronsted acidic site. So, and also if we can dope with metal, so then Lewis acidic site will be developed, and this tangible synergistic effect of Bronsted and Lewis acidic site of protonated and metal doped. Remember, protonated from graphene oxide and metal doping can give you Lewis acidic property. So protonation for Bronsted acidic site. So there will be a tangible effect, and that can be possibly utilized. That we demonstrated in a particular reaction, in a nickel catalyzed reaction, where nickel is pretty stable because possibly the macroporous pores where nickel can reside upon, and being supported by this graphene oxide, which is converted during the solvothermal process to reduce graphene oxide finally. So pi electron rich surface as well as the macroporous, porous zeolite can stabilize the nickel 0. And indeed, we are able to show it in a 1,3 dipolar cycloaddition reaction in multi-component reaction from halide, azide to azide, and reacting with this in a regioselective manner. And surprisingly, till now, only 3 or 4 examples of nickel catalyzed, because copper is well known because it is called copper catalyzed azide alkyne cycloaddition reaction developed by Ken-Barry surplus as a click reaction. But when people use Rennie nickel, it lacks regioselectivity because 1,2 and 1,4 and 1,5 disubstituted species are formed. And then there are some cyclopentadienyl nickel complex with Janfos ligand, the precious nickel source ligand, etc. regioselective preference to 1,5 dicer, not 1,4. This is 1,5. And 1,4 is this one. 1, 2, 3, 4. Triazole system. And very recently, last year in green chemistry, there is a publication with nickel triazole-based organic polymer was used for this system. So we used here the hexagonal, zeolite embedded with reduced graphene oxide, where nickel can reside on the pores, so that this is used in the 1,3 dipolar cycloaddition reaction, and this is much better. Nickel reduced graphene oxide zeolite is much better than nickel reduced graphene oxide or nickel zeolite or other nickel reported catalyst. And we found it, and as you can see, it is a 52% yield, 40% yield, and 77 to 94% yield in a very regioselective manner in a 3-component process. So all of this is summarized here in a table of content data that halide, azide, and alkyne, terminal alkyne, can be used with this nickel reduced graphene oxide zeolite catalyst to get this regioselective triazole synthesis. Nickel-based regioselective catalyst for high yield triazole in water, so aqueous medium. So all these characterization preparations, and if you are interested, you can see this paper, which is now it is open access because material advances has been introduced in the last year. So it is still now open access, so one can download this one and get through details of these processes. So with this, I like to, the summary of my talk is that it is graphene oxide is easily obtainable and sustainable carbonaceous material, and can be used as a metal-free carbocatalyst in diverse organic reactions that I have shown you. Then reduced graphene oxide, one can get it by using different sources, both chemical, servothermal, or biological sources, and they have slightly different properties, and one can use it very biological sources or extracts for use for its preparation. And RGO can be used as a stabilized nickel zero material, apply in Koryo-Kumada reaction or carbon sulfur coupling reactions. And there is a synergism offered by manganese dioxide and electron-rich amine functionalized graphene nanosets to reduce the quantum of oxidative agents in heterogeneous oxidation process. And finally, nickel zero is further stabilized because from here, from these two reactions, we had some problem because nickel zero during reaction or after the reaction could be oxidized. But here, it is further stabilized with this new composite from RGO and zeolite, or rather geozeolite, which in situ converted to reduced graphene oxide. So new composite, ternary composite, nickel RGO zeolite that has been prepared, characterized, and used in regioselective on-water 1,3 dipolar cycloaddition reactions. With this, I like to show some of my students who did all of these works. Some of them are here, and I had collaboration with, and this Dr. Pralay Das is in Himachal Pradesh now in CSIR IHBT lab, and others are working at different places. All of them have been awarded PhD and working in different colleges, universities, and research institutions. And the money that we got from different funding agencies like DST, SERB, CSIR, or my university, erstwhile University of North Bengal. And I must show you my collaborators with whom I have indebted to. One side, my students, who are really brilliant and hardworking and motivated. And the other side, my 3 collaborators with whom I was happy to collaborate and found nice result. One is the former head of this CGCRI, Central Glass and Ceramic Research. Presently, he is a emeritus scientist in Satyen Bose National Research Center in Calcutta. And then one of my friends in Sweden, Fredrik Alquist, from Umeå University, Sweden. We had some patent also ultimately with palladium catalyst with this. And the last one, who is a very big shot and one of the editor-in-chief in Asia Central Science Journal presently, Professor Dongyan Zhao, in Fudan University, Shanghai, where I also visited 3 times, and we published jointly one paper with him during 2015-16 I visited. So with this, I must thank you all for your kind attention and listening to my talk. Thank you.
Thank you so much, sir. I think our participants learned many things about this graphene, means what is the difference between graphene and graphite, and the synthesis of graphene and graphene oxide, and then reduced graphene oxide, and then by using this graphene oxide as a catalyst, means you have synthesized different. You have synthesized and you have applied this graphene oxide for the for the oxidation of these alcohols, and then you have used this graphene oxide for the CH activation, and then from the reduction of nitro to amine, and then you have synthesized this reduced graphene oxide, and then amine functionalized graphene oxide. You have showed the preparation and its application. Then you have showed the importance of flow chemistry. Then you have synthesized, you have showed the synthesis of manganese dioxide functionalized, and then functionalized amine functionalized graphene oxide, and then you have used this for the oxidation of alcohols. Then metal dope. Recently, you have published this nickel dope zeolite for as a catalyst, heterogeneous catalyst for the synthesis of triazole in water. So with this, I think our participants definitely learned many things about this heterogeneous catalyst, and you have characterized all these. You have prepared those catalysts. So now I am requesting any participants, if you want to share your views, or if you have any questions, please ask directly to sir, because it's a good opportunity for you people to interact with sir. Now I'm requesting Aditi Sharma.
Good afternoon, sir. I'm audible?
Yes.
Hello. Good afternoon, sir.
Yes.
I'm audible?
Yes.
Okay, good afternoon, sir. Sir, thank you so much for your lecture. I personally enjoyed your lecture, and literally I learned so many things, so many new things, especially I mentioned new things. And thank you so much for your effort and your time. And it's my honor to interact with you and personally talk to you. And thank you so much, sir. And
Okay, thank you.
Thank you, Aditi. Now I'm requesting Neha Bansal.
Good afternoon, sir.
Good
Thank you
afternoon.
so much, sir. Thank you so much, sir, for such an informative and very nice presentation. Actually, the topic is new for me, but the way you presented it, I find it very interesting and informative. Thank you once again.
Welcome. You are welcome.
Rajvinder. Any student from MSc 4th, because this graphene and this carbon nanotubes all are in your syllabus. Any student from MSc 4th? Manmi, Rajvinder.
Yes, sir. Good afternoon, sir. Sir, am I audible?
Yes.
Yes.
Oh, okay, sir. So thank you for giving us informative presentation, because we get a lot of new ideas related to nanotechnology, which is a very current topic in today's era. Therefore, your presentation has a very good impact on, and definitely it will be worthwhile for us to attend your presentation. Thank you, sir.
Okay, you are welcome. Only thing, if you have any question, because it is included in your syllabus. So if you have any question, write to me to my email address at gmail.com. So just introducing yourself and then write to me so that I can get if you have any questions afterwards. Not right now, maybe later.
Okay, sir. Definitely, sir.
Yeah. And this is my mobile number also, which is also having the WhatsApp. So you can send your questions here too. I know you are tired listening lectures since morning. So maybe you like to, quit. So if you do not have much questions, so it is better we should quit. But anyway, we are not disconnecting totally. I have a mobile number and the email address. So you can write to me giving your, introduction and then your questions. I would be able to see, and I will try my best to get back to you with possible answers.
Thank you so much, sir. So, dear students, you please note sir's contact number or mail ID if you want, and if you have question, you can directly approach to sir. It's a great opportunity for you people at this stage. So, thank you. Now, is there any participants who wants to interact with sir or share your views? So if not, then I am requesting our HOD, Dr. Sandeep, sir, for his kind words as a valedictory note.
Thank you, Dr. Bubu. So on the behalf of entire fraternity of university, especially Department of Chemistry, I would like to express my humble gratitude to our guest of honors for today's one-day national webinar on recent trends in chemistry. Professor Rakesh Sharma ji, Professor Asish Ranjan Das, Professor Anil Kumar, Gopinathan, and Professor Basudeb Basu. They took out time from their busy schedule and give us remarkable insight on such a contemporary topic. It is a matter of great pride and great fortune that such prominent personalities who shared a part of their vast knowledge with us. I thank all the invited guest speakers. I appreciate and acknowledge the participants on this webinar from various institutes whose wholehearted participation made this webinar a success. This type of events can't happen overnight. I have been fortunate to be supported by my esteemed faculty members of Department of Chemistry. With deep sense of appreciation, I would like to thank all of them for their dedication and untiring efforts to make this webinar a success, especially to Dr. Bhuvan Banerjee for taking initiative for this webinar. This event would not be successful without the support and guidance of our Honorable Vice-Chancellor, Sir, Professor Gurmail Singh, the most relevant personality of Akal University. His immense support and constant encouragement motivated us to conduct such an informative webinar. We are grateful to you, sir. Last but not the least, I pass my sincere thanks to the technical team of Akal University whose effort made this event possible, especially to Mr. Sunil ji and Mr. Pradeep Singh ji for their swift responses to our queries and requirements. Once again, I thank all the participants for attending this webinar. Thank you all. Thank you.
Okay, thank you.
So, Dr. Sandeep, now once again, thank you, Professor Basu sir. Thank you for your valuable time. Thanks a lot. And dear participants, thank you so much. Again, this is the third time we are organizing this. This is the third webinar on the same topic, recent trends in green chemistry. So again, in future, if we will organize such webinar, we will definitely let you know. So thank you. Thanks a lot for your participation. Thank you, sir. Thank you once again. So with this, today we should stop here. And thank you so much.
Thank you very much. Thank you. Goodbye.